Okay, so, and we have another 3 minutes to go, and those that, or do you want to do it right now? All right, so this is the ForthOGUST 2020 Zoom meeting, and we write August 2023. Welcome everyone. I hope we will have a very interesting meeting, and exciting talks are on our agenda, which I can show right now. So let's see. Look at the agenda. So we will focus on 2 computers today. That is the minor computer developed by Dennis Kuschel, and he will talk as our first speaker. And then there is another neo-retro computer called the Agon and the Agon Lite. And we will have 2 talks by Phil Waller talking about running FPGA on it, and by myself running old 40 years programs volksForth on it. And of course, we will look into other subjects like ESP32 force and using Qbots for educational purposes, and how to do robot encoders, and look at some mathematics in force. Then we will have a short break, and then we go up for the second part with a hold-on application called PeriMan, and I'm quite excited how to manage the complexity of I/O configuration in that way. We will see how it goes. I saw Bill in the meeting already, so either there is a recorded talk or you will do it online. I don't know, we will decide then. Howard will give us some update on Colorforth, and then we go into a workshop session with Klaus, who will talk about microcore and how to bring up microcore on the boards, but you will decide on the exact things, of course, on your own. So that's our schedule for today, which is quite a lot. And I think it's important for everyone to keep in time, do not talk too long, and try to be as precise as possible to give also everyone the chance to ask questions and allow us for some discussion on the topics, because that's how this meeting lives, and that's always exciting. So, and without further ado, I would like to hand over the camera and the control to Dennis. Dennis, I'm really happy that you are here and talk about your amazing force computer that runs force without an ALU, and we will learn how this is possible by you. So the stage is yours, Dennis.
Thank you, Ulrich. Can you hear me? May I ask?
Yeah, we can hear you.
Okay. Yes, thank you for the invitation. And I will start sharing my screen now. 1 minute. 1 second, I hope. Okay.
That works fine.
This is my screen. You told the community from myForth, minor, I have to correct you, it's myForth. Minor is the predecessor, and myForth is the latest product. I will show you it now. this is my new MyForth board. It's a CPU-less computer design. It is built with 16 CMOS logic chips and 4 memory chips, and it has no ALU. Instead, it uses one single NOR gate to do all the computations. And the rest of the ALU is implemented in software. The board has 32 kilobytes of EEPROM, 11 kilobytes used by the microcontroller, and 21 kilobytes is free for the application, which is Forth in this case. 32 kilobytes SRAM are on the board, and that RAM is also used for all the CPU registers. There are no special chips on the PCB for registers, all is in the RAM. Also, there are 256 kilobytes of EEPROM, which is used for the block storage of Forth. And the processor speed is minimum 8 megahertz, but it can be high as 14 megahertz. The board has some interfaces, a big GPIO interface with parallel I/O, and several pins are reserved for UART and I2C. And the board is very small, it's only 10 by 10 centimeters, which is a really cheap format for producing it in China. More features. The board is controlled via a serial terminal with 4800 baud. It's not fast, but it's okay. The I2C bus can be used to connect external devices. For example, ready available quick and stemmer boards. Digital I/O, 8 inputs and 8 outputs. I mentioned before, some pins are already used by UART and I2C. The power consumption is really low. It's only 0.6 watt. It's because all is in CMOS. There's no LSTTL. It's very, which is very power consuming. It's really all CMOS. So you can power this board also from a small battery. And one important thing, the board is completely populated with THT components. There's no SMD on it. So now I show you the predecessor. This is the minor board. And the special about this board is that this is my first computer that has this one NOR gate ALU. But it has little memory. The memory was the bottleneck for the Forth, so I increased it with the MyForth board. And it is not very slow, very fast. It can be clocked up to 8 megahertz, which is a little bit slow. Here you can see the block diagram. I've colored all the components on the PCB, so you can see which function is where located on the board. And there's really no CPU or microcontroller. There are some registers and some counters, but no CPU, no microcontroller. It's really discrete. Some short facts about the CPU. The EEPROM contains the microcode as well as the application program, and a micro instruction is 16-bit wide. We will see it later. A micro instruction cycle has 2 phases. In the first phase, the 8-bit control word is loaded from the EEPROM into the control word ledge. The control word defines the source and the destination of the following data flow cycle. In the second phase, the transfer of the data takes place. The data sources are EEPROM, SRAM, data register, and the input register. The data sinks are SRAM, data register, the NOR gate, address register, instruction register, and the output register. If the EEPROM is the data source, the upper 8 bits of the micro instruction can be used as a constant value. This is used e.g. for addressing registers in the RAM, like the PC or the stack pointer. Microcode can perform a conditional jumps within the range of 128 microinstructions, and this makes it possible to construct loops to perform 8-bit operations on the single NOR gate. CPU registers are stored in the RAM, PC stack point accumulator, and some other registers. And this is how the ALU really works. I have really only one NOR gate, which does all the tasks. MyForth has only one data transfer register for temporary data storage, and I have connected the NOR gate to the data lane 0. All logic functions that need to combine two data sources are routed through this gate. Additions can be performed by repetitive operation of this NOR gate. Same for AND, OR, XOR, etc. And the other simple ALU functions are implemented as lookup tables in the EEPROM. There are tables for incrementing, decrementing, left and right rotating, and for zero testing a byte. Here's an example of how the rotation is done with lookup tables. It takes 3 micro instructions with 6 clock cycles to rotate 1 byte in the data register. In the first step, the data is loaded into a temporary register, which allows to map the data to address lines 0 to 7 of the EEPROM. Then the idea of the table that shall be used, which is the rotation table in this case, is loaded into a second register. And the output of this register is applied to the lines A8 to A14. And in the third instruction cycle, the rotation takes place and the data is stored in the output register, which is in this case also the data register. One thing to remember, it is important to know that the CPU uses 2 phases. In the first phase, the macro instruction is fetched into the control word latch. And these bits are used in the second phase to define the data source and the destination. In the second phase, the instruction gets executed, which means that data is moved from any source to any destination. And in this second phase, also the EEPROM can be the source. So I can write constant values into the RAM or the data register or the address registers. This makes it possible to do random access to the EEPROM or the SRAM in the system. Do you have questions until now? Other questions? Okay. Then I will show you how I have implemented this CPU. My first thinking about it, my ideas, how I have started to construct this. I thought about having the microcode EEPROM, and to execute these instructions, I need a counter. And I have to apply the opcode to the EEPROM and to select one of the macro instruction tables. Because MyForth has 2 execution phases for each macro instruction, which makes this macro instruction virtually 16-bit wide, we need a register to store the lower 8 bits of the macro instruction in the first execution phase. This control word defines the data source and sink, which is addressed in the second phase. So in this slice, I've added the control word latch and the source and destination decoder. Then I thought about how to address all the RAM. So I needed 2 additional registers to hold the random address. But because we want to be able to run code from RAM, we need to connect the address and the data buses together. This also enables random access to the EEPROM through the 2 address registers. And now we add more connections. The address register and the opcode register can be loaded with data from the RAM and the EEPROM. And the macro instruction counter can be loaded from the lower part of the address register. And this is important to know because this has one advantage. The content of the data transfer register, which you can still not see in this diagram, is not altered when the microcode counter must be updated for loops, for example. So this is one more degree you have to store data, and it makes things much simpler. Now we are at the LLU. The data register is the only register on the databus that can store temporary values. That is here. The data register not only stores the result of the NOR gate operation, but it also serves as storage for data to be copied from one RAM cell to another cell in RAM. So in the system, I need a storage space, one point, one place where I can store temporary values, e.g. when I want to copy data from RAM to RAM. So this is also performed with the data register, which can be compared to the accumulator when you, for LO operations. The computer still needs some I/O, which we'll add now. And last but not least, we have to add some interconnections and some glue logic. And then we're finished. This is the CPU design. There's one conditional load line or signal, and the phase signal which interconnects everything. And that's the magic. This is the whole schematics. It's not much. And now I will try to explain the micro instruction format and how the micro code works. As I said before, the code word is 16-bit wide, and the lower 8 bits are encoding the source and the destination of the data flow in the second phase. And 6 bits are used to decode the direction, and 2 bits have a special meaning. There's 1 bit that is used to reset the NOR gate, the input flip-flop of the NOR gate, so it makes it a bit faster for some LLU functions when it's not needed to write a 0 into the NOR gate input register. And there's one further bit which is important. That's the load counter bit. When this bit is set, depending on the value of the NOR gate input flip-flop, a new address is loaded into the micro instruction counter, or not if the bit is not set. So it's possible to do a conditional jump within the microcode itself. And this is how the microcode looks like. I've written this microcode compiler in C. So all this you can see are macros, and here's a code fragment that is very often used in my microcode. It increments the PC, the program counter, and you can see how many instructions are needed to only increment the PC, the first byte of the PC. I did this this way. I first incremented the PC, then tested it for overflow. If the PCL is 0, there was an overflow, and I have to increment also the upper part of the program counter. And here's the conditional jump. If there was no overflow, this following block is not executed. The CPU jumps behind this block, and there follows the rest of the instruction. And when you look closer to this, you see that the machine does only move data from one point to another. This is always move data from anywhere. In this case, it's a constant. And this constant is written to the address register higher value, higher part. This is also a constant. This is the memory cell. and then the memory gets read into the address low register again, which is then used as index into the incrementation table. Then the EEPROM is read. The incremented value is stored in the data register. Then the memory cell for the PC low is applied to the address lines of the RAM, and the result, the incremented PC low, is written back to memory. And this is why the PC, why my computer is so slow. There are many instructions needed to perform a simple task. If you like, you can download this microcode from my website and have a closer look to it. All is open source and all is available on my website. It might be that you can't find it because it's a bit hidden. So if you don't find it, please ask me. I will point you to the download link. Now I would like to talk about the FORTH stack. The FORTH stack is my FORTH board with keyboard and display. The FORTH stack features, it has a big display, it has a full-sized keyboard, and it has a 3D printed housing. As I mentioned before, the power consumption of my computer is so low that it is easy to power it by battery. And oh, sorry, I got an audio problem. One moment. Yes, okay. Smallest possible size. The size is defined by the keyboard. I would like to have it done a bit smaller, but I can't reduce the size because the display has this size. The size is only 20 by 12 by 3.5 centimeters. It's really small. And the interfaces are accessible at the rear side. I will show you it in a few minutes. The FORTH stack consists of the myFORTH computer board and the additional PCB. And this additional PCB adds only one more CMOS logic chip to the design. So I have tried to cap the amount of required chips as low as possible. This is how it looks like inside. It's a myFORTH board plus the display and the keyboard. And on the right side, you can see how it's put into the case. Here's an example of the built-in editor. I have an editor in the ROM, so it's possible to write your own source code when you are on the go on this FORTH stack. So you do not need a PC with terminal or so, but you can write your code directly on the FORTH stack. It's a really portable device. Some words about the FORTH system itself. myFORTH implements the FORTH 2012 standard. It's a 16-bit FORTH system, which uses subroutine threaded code because it's much faster to run assembly code. I can't do indirection data lookups via pointers in the CPU because it's too slow. I would have to implement lots additions to indirectly address the RAM cells, and adding is really, really slow. So I have implemented it with subroutine threaded code. The FORTH kernel is written completely in machine language. I have block storage in optional EEPROMs. And there's an integrated text editor, one for the LCD and one for the terminal. There are two text editors implemented in the system. Easy data transfer to a PC via RS-232 and a transfer tool. So it's possible to exchange files, your screens or memory, binary memory blocks with an additional tool that runs under Linux, Windows, or macOS. And you can write also your screens on your PC, and you can then transfer them to the Forth tag or the MyForth board via RS-232 and the external tool. Supported words are the core extension words, double number words, and the block word set. And I have implemented some more words, which doesn't fit into the EEPROM because the EEPROM is really full. There's no space left for extensions. But I've implemented a mechanism to load extensions from EEPROM into the RAM. So I can write binary extension modules. And I have written 3 modules already. One contains the string word set, one the floating point word set, and one the facility word set. There are some special words that are specific to MyForth. This is the editor and the terminal and LCD word to switch between terminal and LCD mode. Then I have some words for I2C, then for the I/O port, then the B-load board that loads this binary extension modules, and I have implemented 3 words that allow you to save a binary image from the dictionary to the EEPROM and load them back. So if you have an application developed on the board, you do not need to compile it all again when you switch on the board. This takes really long time. So you can write your application, compile it, and then save it as an image. And if you need the application, you switch on the board and load the image and run it. It's much faster than compiling it every time. Here are 2 examples. On the right, you can see some examples with the floating point words. I will show you it in a few minutes on the real board. It works really, really well. I have implemented the the floating point system that the Jörg Völker has developed. He calls it FlexiFloat, and this works pretty well. It's really good. It's not very exact. It has only 23 bits and not 24 bits in the Mantissa, but 23 bits are enough. It's good enough. MyForth for minor. When I was developing the Forth for the MyForth board, someone wrote me an email and told me that he has only built the minor board yet, but he wanted to try out MyForth on this board. Okay, then I've cross-compiled it for my other board and made a special Forth version, a special ROM version for the minor computer. But because the minor board is completely compatible to the transistor computer that I've built, this special Forth version runs also on my transistor computer. In the picture you see the transistor computer, which has 2,495 transistors. It's a really compact device. It's not really big. The display you can see is not supported by the Forth. It's yeah, it's only to show that this transistor computer can also be used to play games. If you're interested in this computer design, you can visit my website, and there you can also download the MyForth for this transistor computer. Yes, this was my presentation. Thank you for listening. But I will show you now in reality how my system works. One moment.
So, erst einmal super. Danke für deinen Vortrag. Thanks for the talk. And yeah, let's see how the presentation works.
A big applause for Dennis. Fantastic.
Dennis, yeah, great.
Thank you.
Yeah, excellent.
Do you have any questions until now we can talk about? Or shall I continue to show you the system? And it's easy done. You see the MyForth board here in the picture. And I've connected already a display and a temperature sensor via I2C. I power it on. In the terminal, you see the welcome message. You see that there's only one EEPROM installed. There is one socket not populated. There are many words already installed in the EEPROM. And really, it's FORTH. I can show you. I can prove it. Yes. Hello world. This is the content of the EEPROM. There are some demo programs. I show you the editor. It's a really simple editor. It's not very comfortable to work with, but it's possible to edit. So you type the number, the line number, and then you can change something. It's not really comfortable. So now let's load this demo. It's really slow, I said it before, but it works. That's the important thing about it. All my programs have one special word defined, it's the run word. All my programs are executed with entering run. Oh, there's one problem I see. You can't see the display. And this is because my camera is not working. Okay, that's a problem. One moment, I have to reset the camera.
In between, Atle can ask a question.
Yes, yes, of course.
Now, I'm just sitting here and gaping at this, and I'm wondering, where on earth did you get the inspiration from this? Did you look at some old, early computers from the 1940s, or where did you get the idea?
The idea, this is not the first project I made. I have also another really big project that I call my CPU. It's also a discrete computer, discrete CPU computer. And this project was started many years ago when I was still on university. And after many years, I decided to start a new project, a much simpler project, which has much less parts. And then I stumbled about FORTH and thought it would be a really great idea to have a simple device which has FORTH in RAM. So you can switch it on like the old computers in the 1980s that had a basic interpreter. And I wanted to build something like that, but with FORTH and LCD and display. So I started my FORTH with the goal in mind to have the FORTH stack finally, and yes, this was my goal. My goal was really to have the FORTH stack And it took not really long. The development took about half a year. That was not so difficult. One moment, I have to.
It's absolutely brilliant.
Thank you.
This is exactly my question also. So thank you very much, Atle.
Okay, thank you. So I have the camera back on.
Dennis, but half a year work, how many hours you
Oh, many.
You spend many hours, yeah.
Many hours. I have 2 children, so at home I have little time. In the evening I have 2 hours maximum when the kids are in the beds. So yes, hard work every evening and weekends, and at work in the lunch break I worked also on the software. So hard work over half a year. So there it is. The camera is working again. And you see in the terminal the temperature and the humidity, the same that is printed on the display. And when I heat up the sensor, the display should change. Yes, it changes the color. Yes, it works.
You mentioned that there's only one EEPROM, but I only see one socket. If you put more than one, do you somehow are you able to like stack them on top of each other?
You mean the EEPROM?
Yes.
Yes, the EEPROM. You can populate a second one there. Then you have 256 kilobytes of memory.
Okay.
But it is possible to add up to 8 EEPROMs of the smallest possible type. It's the 24LC 512. If you take 8 of these, then you can install up to 512 kilobytes. And that's a lot, I think, for such a little system. So
is it becoming difficult to get these components?
No. I had some experiences already with my CPU, and the problem was that over the years many components were discontinued. So my goal was when I started developing MyForth that I only use components that are already or that are still in production, that you can buy at any distributor like Moser or DigiKey. So it's possible to get or to source all these components from the fabric. There's no need to search eBay for discontinued parts.
Just one more thing. With that I2C bus that you have to write the drivers in MyForth. How many drivers do you have? How many I2C boards have you written drivers for?
I by myself have written 4 drivers for different LCDs and temperature sensors, but there are some other people already writing drivers. So there is an increasing number of drivers available. And feel free to write also drivers for my system. I'm glad about every contribution. So yes.
Dennis, I think in our group there are already 4 or almost half a dozen boards built from your system.
Oha, it's much. Okay. This is the 4th deck. It's a really small device, I said before. You can see I can really hold it in hands and type on the tiny keyboard. It's really comfortable anyways. I have a small demo program that prints the time and date. there's an RTC board inside installed. It's from, I think, it's a stemmer board, but I don't know the number, the ordering number. Yes, any key ends this demo. The neat thing is you can use this fourth deck as a scientific calculator. There's the floating point where it's loaded. For example, when I enter some equations, and it's not slow. It's not very fast, but it's fast enough, I think. That's the result. I've also implemented sinus and cosinus and other floating point words. Yeah. My mistake. I still missed the E. So, and it's not slow. I think it's fast enough. So you can use it as a scientific calculator at work or where else. It's really a nice thing. Do you know the game 248? I can show you. Here's my index. Some extension modules installed in the EEPROM and also the game. This is the editor on the fourth deck. It's simple, but it's really usable. It's much better than the editor in the terminal. This editor also allows you to insert text. The terminal editor could only overwrite text, but couldn't insert text. So this is much more comfortable.
Dennis, is this a block editor?
This is a block editor, yes. It's block oriented. So you see the block number here in this corner. I will show you also the source code of the game. It's starting at block 10 or screen 10. There. This is the code of the game. It's a bit compressed. It's not a bit, it's really compressed. This is the one. One thing is missing. I can't jump to the next block. I have to leave the editor. But there's still room for improvement. So let's load the game. The game has many lines of code, so it takes a while. This is only for demonstration. Normally, I save the game as binary image and can load it then back from EEPROM. It's much faster. The game is really playable. You have to wait a bit after pressing a button, but it's not so long. In this game, the goal is to sum up the cells that way that you get one cell that contains the value 2048. There's also one thing. What's missing until now? I've only one game, that is this one, and I'm no game developer. So feel free to support me with your games. I would like to have some more games, but I by myself do not have the time, and it's not the thing I like to do is writing games. But I also do not play games, by the way. It works, yes. One thing. Okay. I can show you how to save the binary file. You can save it by simply entering save image. So I make a complete image. I save a complete image of the dictionary into the EEPROM. It takes a while. The image is huge because also the floating point word set is in there. Oh, 17 kilobytes. Really huge.
That is so huge, 17 kilobytes. I'm working with Android systems, which require 240 gigabytes. It's a slight difference.
Yes.
This is so cool. This is like taking me back to when I started programming. So wonderful. Would you say that you know every bit and every wire in the system?
Yes,
yeah, that is not usual these days.
Yes, of course. I'm just wondering why it's not possible to run.
Oh, I can explain that. It's because you're trying to demonstrate it. It will never work. Don't worry.
Yes. I think yes, that's right.
Oh, something went wrong. Never mind.
Which makes it a pleasant device because it obviously is aware of the situation.
Yes. But the auto start is still working. Okay. I've overwritten the original image. Okay, so the auto start mechanism no loads the image I've or just saved to the EEPROM. So let's wait.
Good.
Well, while we're waiting,
there's the game.
Yeah.
Yeah. Okay. That was my demonstration.
Right. Thank you very much.
Fantastic.
It's really amazing. And we have some time for questions. Well, we had some questions in between, but maybe there are additional ones. Klaus. Mike?
Yeah, here I am. So Dennis, what I want to say is I think your core clearly qualifies for Pico core, if not femto core. I mean, you couldn't possibly do it in a more condensed way, I believe. This even beats Chuck's micro hardware that he did for interpreting force. It beats it by quite a number of gates.
That was also my goal. Good. That was my goal. Good to know that I beat all the others. And I can tell you I'm working on a still smaller device. Yes. I want to have the world record. Yes. More questions?
There is a question in the chat from Alvaro. If you can read it.
It's a subroutine force. Why choose this mode or this model?
Yeah, this model, yes, because this is the only way to implement force in a way it's usable. The system is much too slow to do indirect memory addressing. So it's not possible to, okay, it's possible to do additions, but if you have to perform several additions to only execute one fourth word, the system becomes unusable slow. So the only way was to use subroutine threaded code.
Okay, thanks.
Can I ask?
Yes.
Yeah.
Oh, sorry.
So sorry. Can I just ask? You choose a clock of 8 megahertz. Is there a reason for that? Because surely you could run it a lot quicker than that these days.
The fourth deck or the my fourth board can be clocked up to 16 megahertz, but then it's is no more stable.
Ah, okay, okay.
So I tried it out with the minor board, and the minor board can be clocked up to 10 megahertz, but it's no more stable. And I redesigned it and rearranged the gates, so the my fourth board is a bit more stable at higher clock speeds. The clock, the maximum speed is limited by the delay of all gates.
Okay.
So I tried to reduce the amount of gates that are coming, that are connected after each other. So it's the goal is to reduce this logic load, to reduce the path length, so you can clock it much higher. But 16 megahertz is the limit, and
Okay.
you get it not stable at this high frequency.
Okay, thanks.
Klaus, you have a question?
That's probably the raise hand from before.
Okay.
Yes, probably. Oh, yes, I forgot to lower the hand. Sorry.
So, Dennis, are we ready?
Yes.
Okay, then
yes,
we have no more questions. I will continue.
Okay.
If we can share, thank you again very much. This was a wonderful, wonderful presentation. I invited, of course, Andrew Holmes, which gave us a talk about TTL computers, and he cannot do it today, but he will listen very, very interested to the Zoom on YouTube later.
Mm-hmm.
And also Brad Rodriguez, who has a TTL CPU, but he is also on the road these days, and he cannot join us. But of course, next time he will talk about the TTL, his TTL version.
I would like to mention that it's possible to get the MyForce board from the Netherlands, so you can order it, a complete kit with the board and all the all the ICs, CMOS ICs that make up it, and you can also order sockets, and then you can solder it for yourself and make it run. So that's a good way to get hands on it.
Yes, and there's also a seller on eBay.
Okay, great.
And you are always invited, Dennis, for next meetings to participate with the guys here. They are very interested to know anything you develop.
Okay, I will try.
And thank you again.
Yep.
So, guys, next participant, Phil Whaler. The Agon SBC runs FPGA. Phil, are you in the meeting? Hello, Phil Weller. I think Phil is on vacations. I could not receive any answer to my contact. So we go on with Ulrich Hoffmann.
Yeah,
volksForth PM of the Agon Light 2.
Yeah, which is a little bit surprised because I thought the intro to the Agon computer will be done by Phil, and now I have to improvise a little bit. Let me see, how can I share the screen? Oh, well, there is this. I switched. Well, that's nice. I switched somehow the monitors, and now the share screen button is no longer available. That's interesting. There it is. And then let's see. I would like to share this screen. And so what can you see? No, that's not right. Oh my God. So stuck with the setup. Okay. Do you see a browser with a project ForthWorks?
Yes.
Okay, great. It's a multiple screen setup, and I was normally you get a colored frame around the screen you're sharing. That's no longer available here. I would like to make you aware again about Project ForthWorks, and I will put the appropriate link in the chat. It's hosted at the wiki of Forstgesellschaft, and you can see the address at the top here as well. And it's a collection of ideas about Forth, and you can have a look at the page and see how we collected different ideas of how, for example, do the SPI protocol. You go there, you learn about SPI and how it works. And then you also get Forth pseudocode that describes the algorithms that are necessary. And then you get also Forth implementation of how to do this, software or accessing the hardware and things like this. Interesting enough, you see these bit words to access ports in a bitwise way. We will come back to these in just a moment. Yeah, and you are also welcome to participate. And to do this, you go to the page and you can register as a wiki user to the Project ForthWorks page, or for the wiki, that is. And then you are allowed to change pages and add pages. And if you create a new page, then you can describe your idea as well. And you get some guidelines how to do that. You're very welcome. And if you are in doubt how to do it, please contact me and I will guide you through the process. I think the idea of Project ForthWorks is that, well, we have many different systems, and still we want to work together and work on projects in groups and do things in common. And so the idea is to talk about the general principles, to explain the ideas, and then provide different implementations in different Forth systems, in different Forth dialects. So we say it's embrace the difference, don't fight and equalize everything, but embrace the difference. And if you're ESP32 or no Forth or Micrisp or volksForth or GForth developer, you are invited to join and bring in your ideas and show how this is done in your best Forth system. So that's the advertisement block for today. And so let's see, I would like to talk about volksForth on the Agon light board. And so we have to start and see what is the Agon board in the first place. It's a development of Bernardo Kastrup. We see his picture here, who runs as the Byte Attic pseudonym in the retro computing scene. He has built several what I call neo-retro computers, retro style computers with modern technology, a system called Cerberus that has a 6502 and a Z80 system on it, that is sold by the Dutch History of Computing Museum. And his latest development is the Agon light computer. And the nice thing about that is that he made it open hardware, which means everyone can go ahead, take his design, build their own board, populate them, and use it. And this is where Olimex came in, and they bought this. They built the so-called Agon Light 2 board, which is a slight variation of that board, but still compatible to the original one. And so let's have a look at the board itself. It's a neo-retro computing board that has a EZ80 Z80 CPU. It's a 24-bit addressable CPU, so still an 8-bit CPU with 8-bit accumulator and combination of two 8-bit registers to a 16-bit accumulator in very limited sense. Z80 that is. And but it's more in the flavor of a home computer, very similar to the ESP32 4 station that I talked about, because it has a VGA connector that you can connect an old style monitor to it. And there's a video processor down here that is actually an ESP32 without any antenna, so it can't do the Wi-Fi stuff. But it's able to generate video signals with the same software, with the firmware FPGA that is running also on the ESP32 4 station. So, but the only purpose of this is really generate video signals. It's and handle the keyboard that is connected here. It's actually a PS2 keyboard, although this is a USB connector. Anyway. You can connect a keyboard here, you can connect a monitor here, some audio equipment here if you want to, power supply on the right side, and all the mass storage is located on an SD card that you put in here, and then you can go ahead and run programs. There's a port of BBC Basic to it, and there's also a native Forth port to it, which we can look at some later time. Yeah, maybe that's it. There is several ports, and Olimex added the UX port because they have a family of modules with standardized connectors that you can connect to these UX port, something that is not available in the original version. So it's this EZ80 and it runs at 20 megahertz. So it should perform like 5 times as fast as the home computers of the old era. And it has 128 kilobytes of flash and some SRAM in it, and it can address 24 bits of memory. Or with a bus of 24 bits, and so it comes with a well-equipped amount of SRAM. So you can look up at the Olimex page and have a look at it. It has a Z80, so the natural question is, will it run CP/M? And yes, it does. So there is a Nihiresh that is let's see, well, you get this, Alexander Sharikin, who had the same idea and says, well, yes, have a look at CP/M from Digital Research and build up a layer that connects to the Agon board and allow us to run it in an appropriate way. So he worked a lot on CP/M, and then in the old days, we had also volksForth running on CP/M, and that's what we will look at. volksForth is a 16-bit Forth83 compatible system, and the Forstgesellschaft is actually trying to revive the volksForth versions because we have many platforms supported at that time, Atari ST, Z80, which we will look at, 6502, and also on MS-DOS. And so if you want to know more about it, you can go to the GitHub page of volksForth to have a look at that. Right. And so now I bring in some pictures like this one. It's a desktop picture of the Agon board. And I bring up another thing. So I probably can do it by moving this away. Aha, here we go. Moving this away. And then we get this board, this view here. I can enhance it. And I press the reset button on the board. So we have a look at it. Actually, I didn't connect a proper VGA monitor to it, but much more complicated equipment, a VGA to HDMI converter that is connected here to the port. And then there's an HDMI converter that mimics a USB camera. So, and then I can feed it back to the laptop that I have, and so we can see the what is supposed to run on displayed on the VGA monitor here in the window. So much more complicated setup than the whole computer. And the camera is just a camera, USB camera that is on top and that monitors what's going on. So if you reboot the Agon computer, you are in something, I have to use the other keyboard, which is the PS2 keyboard, not the laptop one. That mimics some kind of monitor. It's capable of reading the SD card and things like this. And you have directory structures. And for my convenience, I set keyboard 2. Let's see, set keyboard 2. Then I have this German keyboard layout. And then let's go to cpm.old. And CPM is just a program that you can run on the Agon board, like BBC Basic. There's support of BBC Basic and the native Forth port. So if we are here, then we have lots of disk images for CPM disk files, and we can load CPM bin, load cpm.bin, yeah, load cpm.bin, and then we run it, and it boots into CPM, and we have a disk drive A with some CPM programs, and volksForth is actually located at drive D. So if we are here, then we can go ahead and just launch volksForth. And here we go. There's volksForth running, and let's shift this a little bit. And so I would like, this is a self-contained system now. It has mass storage. It has a development system, which is volksForth running on it. And let's have a look at agonport.scr. Yeah, and it has a built-in editor. We can just do this here, 12, that runs and allows me to move around. And the full screen editor has complete control, and it has some nice features. So you can move around with cursor keys, which used to, without cursor keys, with Control SDEX, which is what WordStar did at the old times, but it's fairly fine. And I just learned that gamers use these kind of motion control on their systems all the time still. You can switch between screens. We will look at others later on, and you can add some new lines or you can remove lines. That's easy. So you can move around. You can have an override mode or an insert mode. You can switch between these with Control V. And the nice thing here is maybe the character stack and the line stack, which I will show you. So the character stack works as with Control J KL, which is just keys next to each other. So J pushes on the character stack, and K pops off the character stack. So I can press Control J and Control K again to do things. And yeah, so I can slurp something and I can spit it out at some other place. So I can here, I can move down, I can spit it, whoops, I can spit it out here at this place. Yeah, so that's quite nice and very forthy, because we like stacks, don't we? And the same with the line stack. So you can copy the current line with a Control P, and you can spit it out with Control O, pop it again. So this is how you can copy lines. And so that's, once you're familiar with that, that's quite nice to actually work on that. Yeah, so that's a full screen editor, very capable indeed. It has search and replace and lots of things. Let's see, we say view L, which is the editor command. And this, oh, we see the timestamp. It was developed on November 2nd, 1986. Okay, quite a while ago. And now it runs on modern hardware. So that's nice. And let's see, Agon port screen again, and use Agon port.screen. And let's have a look at screen 1, or yeah, which loads the port configuration, because what's it good if you can run a program or a system that displays something on the screen. You also want to do I/O, and you can look up in the Easy80 data sheet that the device actually has 2 8-bit ports that you can access. And if you look at the image here, the camera image, there's a blue and yellow wire that is connected to ground and one of the port pins that we want to access. And so we have to do some definitions that describe the appropriate addresses. We need to do the initialization to actually do that. And then earlier we saw the no force bit IO words. That's star big, setting a single bit according to a mask in a port. Set big actually clears, bis actually sets, and bigs inverts a bit, and you can retrieve a bit with bit star. So that's the way that no force does this, and I just copied over this idea of accessing this. So once we have these, we can define plus LED to actually set the bit of the connected LED and minus LED appropriately. So if we do this, then we can say minus LED, and you see this LED. I have to load it, of course, and then we see minus LED, and then it switches off, and plus LED switches on, and here we go. The very famous blinking is also possible. So we can access I/O from within volksForth running on a real Z80, not emulated, which is quite nice 40 years after its invention. So that's actually some nice thing. Okay, and and on the other hand, at the old times we had these monochrome monitors, and today everything is colorful, and then we certainly can do this as well. We can have colors, and we can have a status line and output certain things. And we can have a nice prompt that displays the stack content in cyan, and we can do some calculation on it. And if we switch to hex, then it's reflected down in the status line. Very similar to what we had on this MS-DOS version of volksForth. But now everything that can run in color. So I just had a couple of hours to put my hands on the board, and during the development, it was quite nice. And in the preparation of this talk, it turned out all of a sudden I couldn't read the SD card, so I have to investigate in that. So I'm lucky that the demonstration went so far. And that's what it is. It's an old system running in an old environment on a neo-retro computer, and it allows to access I/O ports. And EZ80 is a system on a chip. It has also some other components in the I2C and what have you is there as well. And yeah, it would be fun playing around with that system and using the fully self-contained environment to develop things. So now this is a mixed setup, and I have this laptop running so to make it make the appropriate Zoom connection. But the easy setup is very simple. Connect the monitor, connect the keyboard, power up, and that's it. And then you have a self-contained, distraction-free development environment. Very nice. So that's what I wanted to talk about, and I'm open for questions. Thank you very much.
Wonderful, Ulrich. Excellent.
Are there any questions?
Can I ask a quick question about the volksForth terminal that I saw you using there? Is that the one that I could connect to any Forth on a serial line and use? Is there some?
Actually, in my setup, there is no serial line involved. I have a PS2 keyboard like this, yeah, connected to the board that goes into this connector, and there's a VGA output, and then there's some video magic making it appear on my laptop screen. So there's no serial line.
I think it was the earlier board you were showing that was connected via terminal. Am I wrong?
Yeah, well, of course, in principle, the EZ80 also has a serial line, and you could connect to it if you want to. Yeah, but I think that's not the intention. The intention is really have a self-contained system that is like a home computer of the old times that you just use on your own without connecting it to a UX module from Olimex that has a Wi-Fi 8266 chip on it and made the Agon connect to the internet. Yeah, well, you can do it. Yeah. You can do it. Unfortunately, the ESP32 has the capability of Wi-Fi as well, but since there are no antennas connected, you're better don't use it. Otherwise, you fry the chip. Yep. Anyway.
Yeah, excellent. Superb. I love it.
Yeah. So
Dan has a question.
Yep.
Is the keyboard language dependent, so to speak? So you have to have a certain language version?
Yeah. It's configurable. It boots up with a US keyboard layout, and I just did at the beginning. I did within the monitor. I did a set keyboard 2, which switches the keyboard handling to German keyboard, which is what I use. And I think that there's something like a dozen languages supported. So I think Danish will also work.
Thank you.
Mm-hmm. Yeah. So I was really happy. Even I used volksForth, didn't use volksForth extensively for quite a long time. It felt so familiar and so easy to use. And having a system self-contained where the editor and the block storage is on the system, yeah, then it's much easier. And also I reappreciated the block editor that we invented at that time, and because of the character and line stack, I think that's really still a very nice idea, and you get quite fast editing blocks with this. Right. So if there are no further questions, then thank you very much for listening to my talk and my presentation. And we will continue.
We have Ulrich. We have Leonard in the chat.
Mm-hmm.
Leonard is without mic, so he's not making questions.
I can see it.
Okay.
Yeah. You can also auto-run commands in auto-exec text file, like setting the keyboard and starting CPM. I did this, and interesting enough, when I actually started CPM, it has some key presses, most likely from the initialization of the board, still in the keyboard buffer. It starts up with some googly gooks characters on the keyboard, and then yeah, you can start CPM. Obviously, I want to start volksForth directly. And well, then let's talk about the future. I know that you've been working on a native system for the Agon board, and we also want to see whether we can bring up volksForth there, removing the requirement of having CPM booted.
Leonard, we are very happy to have you in the meeting and invite you for next time, if you wish, to show your force on the board. And if you have a contact to Phil Whaler or somebody else in your group who wants to show us force running on this little board, we will be very happy for the next meeting.
Yeah. Especially, I like that there's a 16-bit version and a 24-bit version of that native force, and it would be great to have a look at that.
Very cool.
Yeah.
Okay. Then this was another fantastic presentation of Ulrich, and we are so glad he presented again something new for the group. And our next participant with a robotics presentation is Mindaugas Lunekas, and he will show us Qbots, educational robots, run ESP32 force.
Hello. Hello, everyone. So many participants. It's great to be here. Really nice opportunity. Thank you for that. So I'll just make it short. It's quite an interesting story. Basically, I suppose I can introduce myself a little bit before. My name is Mindaugas. Well, it's Lunekas. I'm from Lithuania, in Eastern Europe. So I'm an associate professor in Vilnius Gediminas Technical University. I teach mechatronics, automation, a little bit of this and a little bit of that. But basically, I studied robotics for my master's and my PhD. And I loved it. And now I continue building robots every day. And one of my inventions is Qbot, is this little educational robot. Now, you might ask, why am I here? Well, originally, this Qbot runs on Arduino, but everything changed when one person ordered the Qbot and decided to rebuild it. Well, which is basically one of the ideas to build educational robotic platforms for people to modify and change and to do something. So one person named Daniel Goribon ordered the Qbot and decided to take everything out of the Qbot and put an SP32 microcontroller inside and try to control it with a different control system. And I'll try to share my screen just to show what he did. I'm not going to go into detail too much about it, but basically he said that it's not a secret, everybody can use it, and he just built a new control system for the Qbot. Basically started everything with, you know, SP32 microcontroller. So he wanted to control the servo motors inside the robot. So in Qbot, I use servo motors both for wheels and for the gripper. So there are 360 servo motors to drive the robot and 180 degrees servo motors to drive the gripper, basically. So he took the SP32 microcontroller along with the H-bridge driver, I think, and started building the control system and started programming. So I'll just show some results that he made. I was really fascinated about this because that's what robotics is all about, is to build a certain control system and to be able to control the robot to accomplish a task. And SP32 is becoming more and more popular these days. So this is really fantastic, I think. So it's very slow, of course, but I mean, it works. It really does perform really well, I think. Oh, 1 sec. I think that was the same. Daniel gave all the code as well, so it's free to use. There's no copyright whatsoever. So it's perhaps all we need is just the control system of S32 microcontroller, and we could upload this code and the Qbot will work. So I'm not going to go through the code, but it doesn't look like a lot of it, just to control the driving and the gripper. So you can, if you want to see or go through the code, you can ask me or contact Daniel directly. He will send all the links, all the code. You can, you know, investigate it, maybe use it or something. I think he did more on it, and I think so now Daniel improved the system, so you can see the driver, you can see the controller. It's completely different control system than originally in the Qbot, which is really nice. Just basically some pictures showing how to connect the controller and the H-bridge driver for the motors. And of course, again, with the new and improved control system, there's a new video, very carefully, but very, very precise. Like the end, so fast. So it can go really slow and it can go really fast, which is what the robot can do. So the very first pictures looked like this. So it was really a mess at the start. So it took Daniel quite a bit of time to build this new system for the Qbot. But as you can see now, it's really nice. So one of the first videos that he made looked like this. Very slow. The wheels are very slow, but the gripper works quite fast. Yep. Here we go. So, well, basically, that's what I wanted to show. Like I said, it's not going to take a long presentation for myself, but I'm really glad to show this, because originally I built Qbots for Arduino and for the kids to learn microcontroller programming. But after Daniel put this new control system into it, I can now see that it's definitely possible to move educational level to a much more sophisticated level of programming. I think this is very important because the microcontroller technology changes over time and it gets better and improves. So if we get stuck with older controllers, there's not much education in it, and now we need to build robots. I believe we need to build newer educational robots that are using the latest microcontroller technologies. So I suppose this is what I wanted to present. It's a really nice result. So thank you so much. Thanks for this opportunity to present my invention. And of course, I will try to answer if you have any questions.
Thank you very much. So are there any questions? So raise hands. So I saw Richard first and then Atle.
Yeah, so this was a 3D printed enclosure, right? Is that
yes?
Yes. Are the files available for that, or is that available to acquire?
Well, I developed these Qbots personally, so they're for sale on the website. But like I said, you can buy just the parts. You can buy the full kit, but it's going to be with Arduino. So if you want to build with SP32 controller, then I suppose the better way is to order just the parts. And some people do that. So they just take the parts and you can rebuild it.
That's nice. Very good.
Okay, thanks.
I build everything at home, so I really love doing this.
There's a question from
my question is it's a little bit about the programming. I saw it move forward and then grab this item.
Yes.
Does it use the ultrasound to know where it is in relation to the item that it grabs?
Yes, that's true. The robot has an ultrasonic sensor in front for its size. And yes, it can detect that object to grab it, and it works. But as much as I can tell, Daniel didn't use the ultrasonic in these videos.
Okay, but would it? What would it have to do in order to distinguish this object from, say, a wall or a box or something? Would it have to move a little bit to the sides to determine the width of the object, or how would it do that?
No, there is no distinguishing. The ultrasonic sensor is just for obstacle detection, basically, object detection, and the distance to the object. If you would want to distinguish that particular object from other objects, yes, then I would do this like you said. I would do a bit of wiggling to the sides and to determine the size of an object. That should make it work. But originally, it just detects the distance to the object, actually.
Excellent, thank you.
Thank you.
I have a question as well. So you say you did this with Arduino, most likely processing, and now this is programmed in Forth. What is your experience and your judgment of using one or the other? Is it easier to understand in Forth, or easier to develop, or what do you think?
Well, Arduino is much easier than Forth, I think. Forth maybe requires more advanced level of programming knowledge. But like I said, I think this is a good way to go, because actually the world is going down. As much as I can see, I work with students a lot. and they're always trying to find easier ways to do everything, which is not a very good approach, I think. Maybe because microcontrollers is not supposed to be easy. I think it's supposed to be efficient and to work well. So SP32, along with the Forth, I think is a more advanced possibility to program educational robots. This could be a way to introduce a newer educational technology, I suppose.
I see. Thank you. So,
Thank you.
Richard.
Yes. Did you have a Scratch interface for this on the Arduino domain?
Sorry.
I know that in the elementary level education that Scratch programming is very popular. So I've actually been wondering about possibly trying to model a Scratch interface for Forth. I think that it wouldn't be especially difficult to try to do that, and that would make Forth a little bit easier for younger students to understand, because you can actually visually see what Forth is doing on the stack. And so I know that Scratch programming is very popular under some IO configurations, and I was wondering if the Qbot had a Scratch interface.
Not really. I use text programming. I
Okay.
grew up on text programming.
Have you seen the Scratch interface? It's the blocks, the drag and drop click blocks that are graphically oriented.
Yes, I
think it would be.
like...
I think that would be very advantageous for making it more
approachable. Yes.
Yes, exactly.
Yes, I suppose there's, in my opinion, there's always supposed to be an easier version and the real programming version, let's say, like this. So it would, yes, I think it would not scare too many students, I suppose.
Yeah, it lowers the barrier for entry, and then
yes,
it also allows you to see both the graphical programming as well as the text. I'm pretty sure you can switch between the two.
Yeah,
and I think that would be a huge advantage there.
This is something I did. There's a buttons on the original PCB that is in the Qbot. I did these high-level commands like move forward, use gripper, turn left, right. This is also for the students, younger students who don't know programming at all. So that's kind of similar to block programming, but it uses the high-level commands. So it's just not to scare with programming, because in my experience, a lot of students afraid of starting robotics because they think that robotics is all about programming, which is like completely false. Robotics is just 25% programming. So I built the educational robot just to like an entry level, like we speak, like just to try to command the robot to do some various tasks, and then you can move one level higher and then another level and so on. So yes, I think starting with very simple commands, then maybe block programming, then text programming, and then take a more advanced controller like SP32, for example.
Mindaugas, let me explain something to Richard. The Scratch is only an interface. It's an editor.
Yes.
You can use the MIT editor to create a Scratch program, and this program will be only of text, composed of text. But you will have these icons. You can play, a child can play with the icons, but this will generate only a text file that you can send to the ESP32 Forth, because the interpreter runs on the chip. So there is nothing to programming work. It's almost nothing, and you can download this for free on the MIT editors.
Yeah.
I think the idea was
this can be implemented in an afternoon. This is no question.
I think the idea was to have something Scratch-like for Forth, or was it?
No, with Forth you can modify the Scratch editor of the MIT with Forth words, and it will work.
Oh, that's great. That's awesome. We should play around with that.
Yeah,
yes.
should have a look at that. Yes.
Yeah.
All right. Are there other questions, comments from?
I can see some comments. I don't know if anybody wants, like William. There are some comments about servo motors. Is there a question there, maybe?
Yeah, there was the question, is it possible to drive the servos directly from the ESP32? There was an answer, yes, it should be when you use it at 3.3 volts or higher. And I said, well, the question is how many servos at the same time?
I think it depends on the control, how many output, GPOs has the SP.
38, I think, 30, almost 30 servos you can control.
Yeah, but you have to have a supply separate from the controller, I suppose.
No, oh, yes. Supply is on 5 volts.
I actually drive servos from 3.7 lithium battery directly. And since they are digital servos, they run pretty well on the lower voltage as well. It's DC motor anyway.
Okay. I think that's it. Thank you very much indeed.
Thank you.
So we stay with robots, and our next speaker is Rob Probin. And Rob, are you in the chat?
Hi. Yes.
Yeah. Then
hello.
Go ahead. Ah, sure.
So hopefully you'll be able to see my screen.
Yes.
Good. So I thought I'd do something on encoders. Encoders are a good way, and you can implement it in several different ways, but they're a good way of finding where your robot is and how fast your robot's going. And if it's an autonomous robot, if it's not being controlled manually, then it's quite typical for robots to have this in. You'll find a lot of toy robots don't have encoders in, and that although you can program them to do simple things, it's difficult to make them reproducible. So I thought I'd give an overview. These parts are available from several hobbyist electronics or robot suppliers. So this is what's called a metal gear motor. This one's got a back shaft where you can fit encoders. So you can see on the these are a bit of a closer view. At the top there's optical encoders which use a infrared or a visual signal, and then it's either reflected or it's blocked. The ones at the bottom have actually got magnets in, and these typically are Hall effect sensors. I'll talk about why these two in a second. They're very good short term. They provide long-term position information. Often you need to combine them. What's called sensor fusion now to figure out where you are long term. They give direct position measurements. So if you've got an accelerometer, although you can integrate your accelerometer, it doesn't make a particularly great solution for position control or for speed control. But you have to be aware that errors accumulate, and there are articles on the web, and I won't repeat that, about the types of errors you get for different types of robots. The robot here, the encoders are on the driven wheels or on the motor shafts of the driven wheels, but you can have things like trailing wheels, and even on Ackermann steering, you can have this sort of system. And just to give you an idea of what you might see, so assume these are counts for each wheel, and you've got an encoder on each wheel. When you're moving straight ahead, obviously you might expect the counts to be equal. When you're making a turn, then obviously the counts are going to be different per wheel. They're also quite good for speed control and acceleration control. So obviously, if you're not getting any pulses per second, then you're stopped. If your left wheel is 100 pulses per second and your right wheel is minus 100, then you're spinning on the spot for a wheelchair type robot. As I just mentioned in my last talk, you need to do some acceleration control in order to stop it slipping, and you can use the encoder system to do that as well. let's have a look at the next sort of more detail. So the one on the left is the magnetic system, but pretty much the magnetic systems tend to have more pulses per rotation. It's not necessarily true. You can have some very fine printed optical systems and fine optics, but those tend to be not present in cheap robots. So you've got the motor here, and on the right of the motor, you've got a sensor board with the Hall effect sensors for magnetic sensors or optical. And then on this Metal Gear motor, there's an extended back shaft from the motor. So you can put your encoder wheel there, of the optical or magnetic wheel on there. And then as the motor spins, it generates pulses into this board, which you feed into the microcontroller. You tend to want, the more resolution you've got, the better. So these are the DC motors, as everybody probably knows, operate at quite high revolutions per minute. And to increase the torque, you run it through a gearbox. And depending on how fast you want your gearbox, so there's a trade-off. Obviously, as you have as you drop down in ratio, the torque drops, but the speed goes up. Because this is spinning fastest compared with the wheels, some for instance, the Micromouse robot competitions or in the line follower competition, some people do put the encoders on the wheels, but you obviously lose the number of pulses if you put the encoder on the wheels is a lot lower, assuming you've got the same sort of output for your encoder than on your motor shaft. So all these are available quite cheaply from electronic suppliers. So they've actually formed, there's a lot of small hobbyist robots that have ended up with these designs. Okay, so let's talk about what sort of pulses you get out of this. So I'm going to show you the situation where you've got either an optical encoder with two sensors, and for optical you've got maybe an infrared LED and then a phototransistor or photodiode, and you've got two pairs of those, but often they're in package. It turns out for this particular sort of robot, some of them actually just get away with one input, right? Because this is an autonomous robot and there's not slopes in the maze or on the line follower, most of the time the software can figure out whether it's going forward or backward. So it's not absolutely necessary to have two for this type of robot, but it's often common because it allows you to differentiate. And the old non-optical mice work this way as well. So if you've got a mouse with a ball at the bottom, or in fact a scroll wheel, often they've got these encoder wheels. What they did on the computer mice is they had a ball that rolled, and then they had two wheels that ran on the ball, and then it drove usually an optical disc that went round and generated pulses, right? And the way it figured out whether it was going forward or back, your mouse was going forward or backwards, is what's called the phase of these signals, right? So if you've got the case of the B lead in the A signal, then you know that it's a forward rotation. And if you've got the A following the B, it's a backwards rotation. And the bit pattern you get out the two are like this. You get 0, 0, 0, 1, 1, 1, 1, 0, sort of a grey code pattern, if you know what that is. You get them in the opposite direction if it's running in the opposite direction. So that allows you to tell direction. I'll just pause there for a second. So this isn't overly complicated, but usually when you first come across it, you scratch your head and figure out how that can possibly work. But it's used in lots and lots of applications. It has been for a long amount of time. So you're getting these pulses into your microcontroller. Before I talk about what we're doing inside those microcontrollers, let me talk about let me just switch topics for a second and talk about the mathematics before we get into some bits of code. So what you end up having to do, if I just skip back to here, is you end up having to do a bunch of calculations, for instance. So to know if you've got a two-wheel mouse, like a wheelchair type design, then you end up having to know how many pulses. You really want to work in some concrete unit like millimeters, right? Not in pulses, not in some sort of arbitrary units. So you end up having to change from how many pulses per second or per fraction of a second, and you might choose some sort of periodic interrupt to estimate the speed and estimate the position and calculate back into, for instance, millimeters. And then you have to obviously take care of the gearbox ratio, and some of them are. It turns out this says 20:1. It's not quite 20:1 when you work it out. You also have got the diameter and the circumference of the wheel to take into account. You've also got the width of the robot when you're rotating. So if you're rotating one forward and one backwards, it's rotating on the spot. If you're doing a turn, so there's a bunch of relatively simple mathematics to get to knowing where you are and how fast you're going. That leads you generally to have to apply some maths to it. Some of those have got fractional parts, right? So before I get into the code, maybe I'll just talk a bit about this. So if you've got, for instance, FlashForth running on runs on the Arduino Nano or similar micros with a 80 mega 328, principally an 8-bit microcontroller, that usually has got a 16-bit cell size in Forth, and it's not really enough scale to do this stuff. You can operate this before we get into what's traditionally done in Forth. There's two other options. One is to use arbitrary scales like 1,000, and you multiply everything by 1,000. The problem with even on these simple robots is the precision when you're calculating out isn't probably enough. You can also do, and I've actually got a bit of this, variable scale integer. So you calculate things in micrometers and then shift it up to different scales. Especially when you're dealing with a limited number of bits, that can end up with complicated code, and you're probably gonna. What ends up is you end up making the problem much more complicated. So the code I'm going to show you is actually out of Zeptoforth on the. It's a Raspberry Pi. It's got the same microprocessor as Raspberry Pi, actually Arduino Nano RP2040. There's other people using that, and in fact I've got some Raspberry Pi Picos as well. And Zeptoforth supports out of the box effectively double cell fixed point arithmetic. And for everybody who hasn't come across this, you have 31 bits or 32 bits of the integer part, a signed integer, and then you've got 32 bits for the fractional part, right? And then you can deal in millimeters, and fractions of a millimeter isn't a problem. If you wanted to operate on FlashForth, then you might be better off using a double cell on FlashForth, which would be an S15.16, and you're probably okay, right? The resolution is probably good enough on the fractional part. What you can do, and I haven't done this in Forth, but there's some C code for this robot that uses single precision on an 18 mega. Now 18 mega's got it hasn't got a lot of support for anything really in terms of integer mathematics, right? But it turns out that the software floating point is fast enough to do these calculations every 2 milliseconds, 500 times a second. So that's possible. I'm actually planning on using single precision Forth on the FlashForth on a microchip PIC 33, a DSP 33. So FlashForth on a PIC 24 and PIC 33 is actually supports single precision floating point. I'll probably choose that over the S1516, and the reason I'll probably do that is, although I'm always as maybe some of us do, I get attracted by interesting problems, right? And both fixed point maths and floating point maths are an interesting problem. The problem is, while you're developing a floating point library or copying bits from Microchip or somebody else, you're not creating a robot, right? So my general advice is, well, what does your environment supply? And it's relatively well catered for. The 18 meg actually on FlashForth. I'd probably, if I had to do it on that platform, which I've got some robots on that, I'd probably just cobble together an S15.16 library. If you've got the luxury of maybe running on a Raspberry Pi run on Linux, where double precision floating point maths, I mean, it's just the calculation time is a rounding error, even if it's doing your software, then sure, if you're going to process power, go for double precision floating point maths. Wasteful, I don't know. Obviously, the other thing that some people point out with floating point maths is you have to be, there is an advantage and disadvantage. Fixed point maths, you have to be careful that you're not falling off the end of precision. With floating point maths, you have to be careful that you're not adding a tiny thing to a larger quantity, because it might be that it just has no effect on the result. You also have to make sure you're not trying to compare for quality, unless you know it's an integer. So floating point numbers will store integers precisely. But if you've done any division specifically, then usually it's not exactly an integer, and you can run into problems when you're trying to compare compare to integers, because it's slightly off. Anyway, I've said enough about scales and programming. I could probably do an entire talk on this. Back to the code and the encoder story. So this, as I mentioned, is actually ZeptoForth. ZeptoForth uses a format like this. Some other forths have, for instance, scientific, a similar format to scientific notation for floating point constants. Actually, this floating point constant is just an alias that I've created for double constant. So just to go through these, you need, because of the wiring on, even on this UK Mars bot, can be different for the polarity. So this tells the rest of the code which way goes forward, right? If you've been consistent, then because one motor is rotated by 180 degrees, the polarity is off. Obviously, you can swap the wiring, and these both would become either negative or positive for the forward direction. That's the polarity. Usually, you find that the wheels have subtly different diameters. And although you want to, if you're going in a straight line along a line following robot or a wall following robot, you want to follow the wall. A good measure is, without any walls, does it approximately go in a straight line, right? If your control system approximately goes in a straight line, then adding steering or those sort of things on becomes a slightly bit easier. And you're not your error control system's not compensating for internal problems. So this rotation bias allows you, even though these tires, and I don't know if this will come off. But this robot here, these are off the shelf Pololu wheels with Pololu rubber, and you'd have thought these were the same diameter, right? But you soon find out that they're not quite. This allows you to adjust that to stop the robot rotating. You want to input the wheel diameter. It's 32 millimeters. So you notice all of these are in human readable constants, right? It helps when you're looking at a debug output, if you're not trying to figure out that it's, 4/16 of some arbitrary unit or some, I don't know, something horrible. So encoder pulses. This is the number of pulses, 12 pulses for one motor revolution. So this is using, this particular robot's using the Hall effect sensors with the magnetic encoders. Gear ratio. So this is the fact that this gear ratio turns out to be not to be exactly 20, but you can set that. And then the mouse radius. This is between the center of the tires. Again, something that you need to potentially tweak. So this is if you're rotating on the, if you're making a curve, then you need to know And this allows you to calculate the effectively angle, right? You notice this code, this is actually my code right now. This has all got constants. Now, the problem with this being constants in Forth is that you probably want to tweak these on the go, right? And you don't want to, these constants are at a quite early stage in the definitions. And you probably don't want to, in terms of Forth, the interactivity is good. So I'm going to replace these actually probably with value, right? With F value, which allows you to write to those things. But obviously when you use them in, they look like constants when you use them in normal code, right? Okay, that's that. So that's the basic sort of constants. Then you need to calculate some higher level stuff, right? So the first one I usually calculate is wheel circumference, which is obviously just pi d. So wheel diameter times pi. You probably want to calculate the number of pulses per wheel rotation, right? Which is encoder pulses times the gear ratio. Let's skip that comment there just for a second. So wheel diameter, right. So once you've got the wheel circumference and the pulses per revolution of the wheel, you can calculate a sort of basic millimeters per count. So this might be a millimeter per count if you're lucky, right? It's unlikely to be a millimeter per count. It never is, right? But and you the more counts. So if you've got a fraction of a millimeter per count, that's better. So the smaller that is. Although for maze solving, specifically, the cell size is 180 millimeters or 18 centimeters. So you can get away with a few millimeters per count, but when you're doing speed calculations, often you've only got a short amount of distance to decelerate. So it's important to have a reasonable resolution. Then these lines here are just for the fact that it's rotation bias. So effectively, it just multiplies these counts. It offsets these counts up and down. So you've got a millimeter per count left and a millimeter per count right. And then you want to calculate. So that gives you the distance that wheel travels. We also want to be able to detect rotation. So some people control each wheel independently, but it's often nice to think about a forward movement and a rotation movement as separate things for control. There is lots of arguments about this in the robot community. I do find it easy to think about angular movement versus an angular speed control over lateral speed, linear speed control. So anyway, this allows you to calculate how many degrees you've turned per millimeter difference. Okay, I'll pause there for a second to allow that to sink into your brains. Okay, so this is the data that shouldn't be there actually. Let's delete that. This is the data for the encoder system. This is the data I've got for the encoder system. So ultimately, I want a distance of the robot, the distance it travels, and I want an angle that it's sitting at out of this encoder system. I'm going to calculate, I've got, as well as some interrupts for the encoders, I've also got a routine that calculates, like a tick routine, 2 milliseconds in the case of this robot. Some people use a fraction of a millisecond, some people use a millisecond. 2 milliseconds is okay. So this is the distance since the last tick, and you'll see that being used in a minute. And then there is a left count and a right count, right? I should tell you a bit about the circuitry before we get onto the next bit of code. So on this particular robot, the connections, this is the connection to the motor. So you've got the true drive signals to the motor that come from a separate piece of circuitry. And then you've got the left, if you remember that graph, we've got a left, we've got an A and a B signal from the two sensors on each side of the robot. And you've got exactly the same on the right. So on this particular robot, it was originally designed although several people, including myself, have put alternative micros on. In the case of this particular one, it was the original robot was designed for an Arduino Nano, which is a 18 mega 328. I'm actually fitting an Arduino Nano RP2040 Connect. Other people are fitting the there's another Nano compatible one called the Maker Pi from Citron. They've put a RP2040 in as well. I think there's actually ESP form factors in with exactly the same sort of ESP32 form factors and exactly the same Nano footprint. So there's a problem with the 328, the original micro, the Arduino Nano. It's effectively, it's only got 2 interrupt inputs. So what we do is we use some XOR gates. I was glad to see some logic gates earlier. I thought it was maybe only us that still use logic gates. So we actually combine these and form a clock signal, right? So whenever one of these changes, effectively you get a change of outputs. This device is a 74HC86. The original design, Rev 1 was listed as a 74LC86, and for everybody who knows a bit about digital TTL logic gates will understand that the LS is really only a 5-volt part, and the Nano IO was 5 volts. The Raspberry Pi Pico Micro, the RP2040 is 3.3 volt IO. It's actually slightly more complicated than that because they've done some things, but we run the whole board rather than have a 5-volt circuit run around the board. We don't fit an auxiliary regulator, so we run the whole board at sensors and everything at 3.3 volts. So we swapped it over to a HC, which is effectively a CMOS equivalent. Okay, so this gives us a clock signal, and we also feed the B into the micro. So we feed this clock signal in and the B into the micro. Now, just to point out before we go any further, some micros, for instance, an example of a robot that I've got is the Microchip PIC 33 DSP. That's got quadrature encoders built in. So some micros can read the outputs of these and provide you. They've got a peripheral that does a lot of this stuff work for you. But where's the fun in that, right? I like writing code. So what I'm going to do here, and the right clock interrupt is exactly the same as this one. So this, and I haven't shown any setup code for the Raspberry Pi Pico. It's not really overly interesting. Whenever we get a change, a rising or falling edge, and we want to use rising and falling edges because that gives us the highest resolution, runs this interrupt. We fetch the 2 signals and XOR it, which effectively gives us the A signal back, right? So we've got A and B. And then we want to do is we want to figure out which way it's going. So the way we do that, and I had to put stat comments in this. I usually see a lot of stat comments as a failure in my fourth programming, but this code's pretty dense. There's not actually way more comments than there is code. So what we want to do is we want to do an XOR of the old A, what it was before, with the new B, and subtract that from the new A with the old B. So we duplicate the 2 readings we've just received. So we've got A and B on the stack, and A and B on the stack. We XOR. We read out old A, which is a variable that only gets set by this routine, and XOR it. We swap over to the other pair, and then we XOR that. So we've got the 2 components, and then we subtract the one from the other, which gives us this delta, multiplied by this adjustment factor. You remember this wheel adjustment factor? And then just add it onto the count. So the count was that variable we saw before. So what you end up with, count just goes up or down based on as you turn the wheel, right? And without another interrupt routine, that's all it would do. So as you turn the wheel, count would go up, and as you turn the wheel the other way, count would go down. And then we store those in the variables for the next go. So this effectively converts from the A and B signal back into a count, because that's really what we want to do. So the next thing, and I'm drastically running out of time here, so this, you'll be glad to know, is the last slide. And maybe I'll talk about something like speed control or acceleration control in one of the future talks. This is a periodic routine. So this really does the job. So these clock signals can arrive, I don't know, maybe 10,000 times a second. So you only want to do sort of minimum amount of work in those. And then every 2 milliseconds, you want to figure out how far the mouse has run in concrete terms. So we obviously want to fetch these counts, and we do a bit of atomic work to reset the counts back to 0. This is the only user. This routine is the only. This interrupt routine is the only user. In fact, you could actually run this on a task. Theoretically, even as FPGA supports sort of high-level tasks, high-priority tasks, and you're probably get away with it. But typically on an interrupt. So you want to fetch 2 counts and 0 them out. So we've got the count since the last 2 millisecond interrupt. We're just going to multiply them by the millimeter per count. So that right away converts these counts into the millimeters that have traveled since the last timer tick, since 2 milliseconds away. Now what we want to do, we really don't want to deal with wheels independently. So we sum the 2 up. Now these, up until this point, this is all integer maths. So we switch from up to floating point maths because we want to divide by a half. That's rather probably, everybody's going to point out I could have used a left shift, but this gives us, this doesn't lose any precision. So we've got effectively we can have sort of we don't lose any. If we just right shifted it by 1, we lose the bottom bit. So here we're not losing the bottom bit, and we store that in forward change. So effectively the 2 wheels, if you add up their millimeters traveled divided by 2, you've got the forward distance traveled. And then we subtract the 2. So whenever the one is different to the other, the robot's turned in some way. So we subtract the 2, and then we multiply it by degrees difference and store that in rotational change. So this gives us, in forward change and rotational change, this gives us a measure of the forward change and the rotational change since the last 2 millisecond interrupts. And we can use that for a bunch of different purposes. For instance, speed control, acceleration control, or angular speed control. We also want to have a cumulative distance, right? So we take these values and add them onto a distance and an angle. So this is an accumulated distance and angle traveled. And that's the end of the presentation for today. Any questions?
Amazing, Rob. Excellent.
So I'll share this on this presentation. I'll share on the FPForth 2020 Facebook group.
Great.
I'll also post a link to the code as well, so you can see all the horrors that are not these routines.
Right. So Atle raised his hands.
Now, I was just wondering, because I recognize that that thing from those rotary encounters to see the faces and so on, but I'm not sure why do you need to do this if you know, because you're controlling the wheels, you're controlling whether they go forward or backward. You're doing that by sending control words to the controller, right? Or am I missing something? I just have a variable that says forward and backward for each one, and every time I set it in forward motion, I set the forward variable, and every time I set backward motion, I set the variable backward. So I have one for each wheel.
You have to open up your mic.
Yes. So I've got an old robot that just has a single input, like you just described that, Lee. So that just has one sensor, and I know whether I'm driving it forward or backwards. I've got a robot that's about 18 years old that does that. There is sometimes a problem where when you're accelerating and decelerating, you can have, there's a certain amount of movement in these gears. It depends on your gear system. And so sometimes you get weird effects where even though you're traveling forward, when you're decelerating, you end up with, especially when you sort of cross it over, where you can have the motor and the wheels have got some play between the two. So I think because these are so cheap, these sensor boards, I mean, they're a few dollars on the Pi Hut or Pi Moroni and similar sites. I think people have just used these because it saves you having to worry about any problems where you might miss a few counts or get it aggregate those counts onto the opposite side. Mm-hmm. So is it absolutely necessary? Because I've driven robots the way it's not used, I can say, well, it's not absolutely necessary, but especially at these robots that can potentially, I mean, this one will only do about 2 meters a second, but if you have a look at some of the competition robots that do 5-6 meters a second and turn at 10G, they try to eliminate all of the control variables as far as you can. And there's always things like dust on the maze board surface and different reflectivity on the walls, and there's a whole bunch of stuff that's variable already. Especially with as faster the robot goes, the more these little things cause problems for the control system and errors. So it's not absolutely necessary, but because these are so cheap and processing it is relatively straightforward, that's typically why people are doing it.
Yeah, so if you look at industrial robots, that's very common. It's called odometry. Measure back the movement and the instructions that you did because of the tolerances that you have in the gear or in the motor or friction or also in the torque and the forces applied by the different motors. So the fabrication tolerances you want to compensate. So you measure back what you instructed the robot to do to see that it actually does what it does. So then you can build up closed loop control to really make the robot do what you want. So I know this from industrial robots, and that's the way they do it.
You never got enough data is the answer. You've never got enough data about the real world.
Well, that's my second question. I have I don't have the pulse counter on the motor itself. I have it on the gear on the wheel.
Yeah.
But I got 24 pulses.
Yeah.
For one revolution. Is that enough? Does that give enough precision to be able to dead reckon where you are? Or
I mean, you need to know how fast your robot's running forward, how fast it's turning, how fast what the size of your robot is, what the size of the wheels are. I mean, if you want to share that information offline on Facebook or directly message me, we can have a discussion about it. It depends is the answer. So certainly some of the Japanese micromice people, when they're doing the half size, or even there's some people that produce quarter size, there isn't enough space to put an encoder on the motor shaft. So they've got no choice but to put it on the wheel. And some of those people are some of the fastest robots in the world, right? I mean, micromouse are the fast ones, not mine. The fast ones are unbelievably fast, right? There's a Veritasium video, I think I shared that, right? So people do make it work is the answer. It's usually not impossible to make things work. I think is the simplest answer I can give for that.
Excellent, thank you. Yeah, I've seen those. They're amazing.
Yeah.
Next question is for Howard, but before I am very concerned because Christian is not making questions this time.
That's right. I'll do one for him.
Yeah, go ahead.
I think it's a quick question that might have a long answer, Rob. I'm just interested to know on what terminal and IDE you use. Did I hear correctly using FPGA on this as well?
Yeah, so I mean, what IDE I'm using right now is, it varies depending on which forth I'm using, right? But I've actually started using, as of a week or two ago, Travis. I'm just trying to convince. Oh, hang on. Let me get out full screen. I think I'm still sharing. Right. Let me just shove this over here. You can see what I've been doing today. Right. So this is Zeptocom, which is Travis's. Now Zeptocom runs in the Chrome browser. It connects to the robot I've just disconnected. Hold on a minute. Let me just plug it back in, and I'll show you it actually running. There you go. Booted up. So this is
what we were talking before the meeting and in the chat with Howard.
Yeah. So this is my. So I'm using this right-hand editor as a scratch pad, right, and just pasting this stuff in like this. I've got my being an old school guy. I've got all my windows over here. So usually I've got two monitors, right? It's a bit of a mess at the moment, but I was actually trying to figure out why I wasn't getting any encoder interrupts actually. But as you can see, I am getting encoder interrupts now. It turns out that I had to debug. I don't know whether I should say this. I found a bug in Travis's code, which is phenomenal code. It's got a giant amount. I ended up writing a visualization for the. Let me show you this. The RP2040 interrupt system. So I wrote some. I mean, this is the great thing with Forth, right? You can just do this on the fly. It's really, you can't with C. You have to end up writing a whole bunch of infrastructure to do this, right? So because I was chasing down this bug with, and said it actually fixed it now. I sent in the information yesterday. I'd written this visualization. So this shows you. This is the. If you're aware of ARM chips, they've got an NVIC interrupt controller, and this is 1 bit per. These are the pending interrupts, and these are the interrupts enabled. So this is the bit, and I've got a thing that prints out which. So 13 is the IRQ bank. So that's that bit there. Pending, that's D is that's the IRQ general interrupt, which is not enabled here but is further down. And then these are the sort of GPIO, and these are the two encoders, right? Rising and falling edge on pin 15 and pin 24. And then you can either type the stuff in down here, or you can like paste it from. If you can't remember the word, you can just go send. You've seen this before. Oh, that's because so let me just load this up. So the one advantage Travis's Zeptocom is he's got an ACK and a NAC, the ASCII characters of it, which means that he can send. It does a restore state, so it can send a whole bunch of. This is all the stuff being sent. So in order for me to get counts out of this, so if I spin the wheels, this is like on-course stuff, right? I have to apologize to Ulrich. So this is, it's not sending counts. And what I want to do is I want to enable a general interrupt, which is probably, that's probably going to do it, I reckon. And if what you'll have seen is the interrupt isn't enabled. There's a pending one. If I show the interrupt status now, you'll see that's set. So it's enabled, and then when I run this thing to look at the counts, there you go. Look, so I'm
okay.
So this is I was twiddling the right wheel. Let me just twiddle the left wheel. So the left wheel is the one on the left, right? So what happens if I go that way? Right. So this is just incrementing count. This isn't the direction. So I was debugging problems with. There was actually a problem with the interrupt masks. It was accessing it as a word. No, sorry, as a byte, and it turns out it basically works sort of, but they're not actually byte addressable, and the hardware does weird things. Travis hadn't spotted this, and I ended up having to write some visualization code so you could just visualize what bits are set and figure out.
Okay, that's excellent news, Rob, because I'm going to have to do an update then, because I'm just starting out having a play with FPGA. And
I mean, he's done loads of stuff. Yeah, PWM. He's got loads of examples.
Yeah,
and I say he's not on the call, so his head won't get too big. But he's a really. I've been impressed because I published a bug and he's fixed it that evening.
Great,
Right.
I would encourage to have a FPGA workshop in one of the upcoming months.
Shut up now.
As there are a couple of people that are interested in using the system, and Travis actually is very helpful in supporting. So to me, this looks like a great way to join forces here.
Yeah, that sounds excellent. Yeah,
right.
Yeah, thanks.
Okay, Travis arrived, and we are going now to a coffee break. And who wants to keep chatting with Travis and with Rob? Go ahead, and we take a break for 10 minutes, Ulrich?
15 minutes, I would say, which means
15 minutes. Perfect.
That's we meet 15 minutes. It's 20 minutes to the hour, whatever hour is your local time zone.
Fantastic. Okay.
Can I just say while you're all here that my picture you can see is of a Raspberry Pi running FPGA, making the LED flash with one line of code. And I got it to work in, I don't know, half an hour. It was so very impressed by the ease of making that work.
As I'm sure Travis would say himself, there's a lot of facilities in it. That's not everybody's cup of tea. But
Rob,
I used Emily Crisp. Go ahead.
Rob
Sorry.
and Travis. So next meeting, if you wish, or in September or October, I invite you to make a workshop about FPGA.
Okay.
So that's the line of code. Sorry about the extra stuff on there. That's because I'm just using a simple serial terminal. I'm not doing anything with the ANSI control characters, but that's what's making the LED flash. So it's, yeah, I'm very impressed with that. I'm very impressed with the chip as well. The RP2040 is just awesome.
There's a lot of facilities on it.
Yep. So I'll be looking forward to getting to know more about that. So there it is. There's the LED flashing there 500 times. Excellent. I'm sorry, I couldn't wait. So I've already got my cup of coffee, so I don't know what. So we can chat. I'm just seeing. I'm seeing the comments in the chat now. I haven't done anything yet. I haven't updated the GPIO interrupt code, so it's not in the build yet, though. Okay, well, I can wait. I don't need interrupts at the moment.
To be honest, I think you won't spot it, right? Because I've been using FPGA for. I used as a work project that. I'm not sure how much I can share. I could check, but I used it as a RF interface, and I've got a PC Python program that talks to a FPGA as an engine, and I did various I/O stuff, SPI and UART and some other stuff as well. I didn't spot any of that.
Mm-hmm.
I've done several other pieces of things, so it might be your by the time. But by the time you get to maybe tweaking specific interrupts and doing that sort of detailed work, because I mean, even for I think Travis, you've got an example of, for instance, NeoPixel, the RGB LED driver. Is that? I guess that's via the PIO, is it? I don't remember, Travis. He seems to be silent. Anyway, so there's a bunch of examples that just work.
Yeah, just to say, I prefer to wait till November as well, because I'm about to move flats. October the 6th is our moving date. So
I hope for a low stress moving date.
there's no such thing.
one of the two most stressful experiences that humans go through. One of them.
Yes,
moving
I'm aware of this. I'm aware of this, but it's a worthwhile move.
Good,
so,
good.
It's good.
What other sensors do you use? A compass in order to have your orientation and so on?
Yeah. So, do I use it? So there are this particular chip, and maybe I can just share that the one I'm actually using is an Arduino Nano RP2040 Connect. Let me just put that in the chat, and that's actually got an accelerometer. It's got a 6-axis IMU, so that's got an accelerometer and a gyroscope on board. Some of them are 9-axis, so they've got magnetic MEMS sensors as well. I'm not sure whether it'll be fast enough to do a lot of real-time control on, because it's connected to an I2C interface rather than SPI. But it will be useful. I'm going to log data from it in order to graph the robot. So one of the things with robots that I actually learned from some of the other robot guys is if you can pull data, store data in RAM or in even on a non-volatile memory of some sort, as long as it's fast enough, and then offline graph it in something like Excel or OpenOffice, you can learn a lot about the robot performance, about the control algorithms, all that sort of stuff. So even if you're not using the accelerometer and gyroscope for control, it's useful because you've got an extra point of reference. Generally, the encoders are pretty good, right? I mean, you can do a lot of work with just encoders and graphing the encoders, and you can see what you can plot your projected speed. For instance, if you've got speed graph, if you remember the speed graph from last time, you can plot your predicted speed against your measured speed from the encoders, and that tells you a lot how your control algorithm, if you've got feed forward components and a feedback component, closed loop as well as open loop control, that can tell you a lot about. And you can turn off one type of control and the other type of control and see how what the profile looks like. It's going to tell you a lot about your control system and how well it's responding and how noisy it is. Because it's difficult if you just put some values, for instance, in a POD control. I talked about this last time. You can end up with something that appears to work, but it's actually quite badly tuned. So plot data is one of the things I learned. But if you've got an accelerator and a gyroscope, then on the MEMS, and they sell them as separate boards as well, tiny little separate boards that you can feed either SPI ones or I2C, and you can feed that data in as well. That gives you an extra data point. There are definitely people who are using those on robots for control. So they do sensor fusion with the encoders and the accelerometer. And then obviously they add in the wall measurement or the line measurement or whatever they're measuring in terms of the environment. And they add these all together in order to form the unified picture. So there are definitely robot people who are using accelerometers and gyroscopes. Also, obviously, there's been, the first time I saw it in sort of a small robot, that they're using them in balance robots. So I think somebody released a balance robot recently. I forget who that was. I saw it advertised, but we've met a guy called Dave Ott from MIT. He's a research assistant. In fact, I think he's been around since the first days at Micromouse. He seems to be an immortal in these parts. And he brought maybe 10 years ago a balance bot that will run. It'll do a line following pattern, and it'll stand up on edge. Obviously, accelerometers and gyroscopes are ideal for that sort of stuff.
I tried to. I built this thing here. I got my compass. On top here.
Yeah.
And then I have these sensors underneath, and then I keep track in order to not have so many interrupts to the processor. I keep track in hardware. I have counters that keep track of the counts in hardware.
Oh.
So when I change direction, then I have to zero the counters, because otherwise it'll just keep counting up. But my problem with that, well, and some bugs and some stuff, but apart from that, the wheels would spin. If I try to go fast, the wheels would spin, and then the dead reckoning would be off. So I'm using these laser sensors. And I have mounted them on servos, so that if it gets confused, this is not for racing, because, but if it gets confused, then it can look around, look behind it, and so on, and try to figure out where it is.
So what do you do for have you got speed control and acceleration control? So obviously it depends on the surface you're running on and what type of wheels on it. Those look like, are they plastic wheels, I guess?
Yeah, everything is plastic. Everything here is from AliExpress.
So I guess if you're running on a very smooth surface, then you want to accelerate the speed. You want to have a smooth acceleration curve, so that you're. I mean, I talked about this last time. So, motor torque's related to current into the motor, but it's actually easy to control acceleration. So if your profile for your speed controller starts at a small speed and then builds up, you probably reduce the amount of wheel spin.
Yeah. No, I just put.
You just put 10 volts on those motors, and they can just go where they want to go.
I put a PWM value there, boom, and then it goes from 0. It accelerates very fast. Okay,
I mean, what you probably, it depends on how far you want to go. I mean, how deep does the rabbit hole go, right? But that's what people typically do. They just put a PWM value on, and you're effectively applying a voltage to the motor, assuming your battery voltage is constant. Because if you're running, obviously the battery voltage dips maybe, and if you PW off the full swing. So, but you're effectively applying a voltage on your motors. So they're gonna the torque is going to be quite high, especially at stall for DC motors, because I think there's a DC motor I saw on the bottom of that. The highest torque is at zero speed. So what you can do instead, if you write some code to control the speed rather than, effectively you want to measure the speed. And what people do, there's several ways of doing speed control as well. There's a whole talk on that, right? But what you can do is, if you've got like a periodic interrupt, measure the position per periodic tick, right? And that position per periodic tick, because it's over time, is a speed measurement. So if you're expecting, 20 encoder pulses per tick, if you're getting less than that, then your speed's not at target. And if you're getting more than that, then your speed's faster, and you need to reduce the PWM voltage. So then you can adjust your voltage output, control your voltage, provide a controller to control the speed of your motors. And then when you've got a speed, you can set a speed. Then it's relatively straightforward then to have an acceleration profile. So you can start at 0, and you go to a particular speed, like maybe 10 millimeters per second, then 20, then 30, and then 40, and you can have a table, and you can actually have a curve if you want. I mean, some of my other robots have, rather than have a linear acceleration, they've got some sort of soft curve at the beginning to try to stop wheels spinning. Yeah, but what you want to probably start doing is, in my opinion anyway, one is to you probably need to compensate for voltage drop in your batteries if you're not running off your motor off a regulator. And then you probably want to control the speed, right? We can talk about some simple ways of doing that, but having effectively something that looks at every time tick, how many pulses you've done, is effectively a speed controller, right?
Yeah, that's a brilliant idea to have this timer that goes and that can do this thing in that timer loop. Yeah, that's
yeah. I mean, you can theoretically do it on variable timer ticks, right? But you gain a whole bunch of complexity because you end up multiplying by time every time, and then you have to make sure that you've got enough timer ticks for it to properly control, and that becomes really, really tricky. Having a fixed timer tick makes a lot of the maths easier.
Yeah. So it looks like, in addition to the ZeptoForce workshop, we also need some kind of robot control workshop.
I think so.
I think that's quite interesting. So I can encourage you to offer this, and then we will put it in one of the upcoming meetings. So that would be great. So Peter, I see you talking. You have to open your mic.
Yes, we have a great opportunity to multiply the force knowledge of this group into new groups now with the Agon computer and with the robotics group, which is growing inside the ForceForth 2020 community. We have two guys. One was today Mindaugas. I can't pronounce his name correctly. Mindaugas is professor in the university for robotics, and then we have Probin, and Atle is so enthusiastic with these things, and other guys. And we have also a French friend who was presented by Mindaugas, which was a great surprise for me. And we have another one from Trinidad and Tobago, as I mentioned before. He made a wonderful video of a bar attendant or a restaurant attendant with a robot, with a platform, moving platform, and he will use probably microcore. He's very interested in using microcore for this robot. And actually he's using Force. He began using Force thanks to our community, to our efforts.
Let's see. Right.
Do you hear me?
Yeah.
Yes.
Yes. Okay. I can say something about the serving robots. In Berlin, there is a Chinese restaurant who were very proud of their serving robot. After about 2 or 3 months, they stopped actually using it. But if there are any kids on a table, then they will send the robot for the kids. But in practical work, it just slows down the wages.
Yes, they had those in a restaurant near us here, and I ended up chasing after it to try and stop it taking something away that I wasn't ready for. It's so very complicated.
So
well,
I think
they don't have microcore. This is the problem, Klaus.
Yeah, probably.
Yeah, not programmed in Forth, definitely.
Yeah. So I think everyone's back from the coffee break. So I would propose that we resume our talks and go on with our next speaker, which is Michel Smart. And he's talking about PeriMan and actually telling us how to manage the complexity of hardware initialization. So, Michael, are you with us?
Yes, I'm here.
Okay, great. Then I will give you the stage. Please go ahead.
Okay. Hello, everyone. Well, I've been following all these chats. They're very interesting to see how everybody's still really engrossed in what they're doing. What am I got? Share my screen. What do
At the bottom row, there's this green share screen button.
Desktop 1. What am I on? I'm because I'm using a Mac. I'm on desktop 3. What does this mean? Oh, sorry about that. Who knows what I'm supposed to get.
Yeah, so there should be at the bottom of the...
Yeah, I've selected share my screen, and now the system has given me a big screen with lots of other things on. Proportional screen, oh dear. I seem to remember last time I used this, I could do, and perhaps I haven't done it. Let me click the share button and see what it says. Oh, it's a system preferences about security. Oh, I need. Clicked on it. System preferences. Oh, here it comes. Oh, privacy. Zoom. Now I click on that. Zoom yes will not be able to record. I don't want it to record. Let me try now what's happening. Share. Right. I've got a picture of, where's my, this one here.
You started screen sharing and we see the whole on screen with
good.
whatever you want to show.
Yes, I thought this would be a good place to start. I've been a big fan of Holon, I would say, since it was invented. So let me see. I've got a lot of other things on this screen. Let me clear that one. So has everybody got a clear view of that, I hope?
Yep.
Yeah, good. So I've had a lot of experience over many years, as you could guess, like most of us, that we've been dabbling or even seriously using Forth. And I've mainly been using the MPE VFX Forth system cross compiler for the last 15 years, I guess. So I'm fairly well into that. And yeah, my other main use is the actual processor family, which has been the STM32 series, which are pretty well known as well. I think one of the biggest ranges of processors available from any supplier. I looked on their webpage just recently, and I think there's about 1,300 variants of the ARM Cortex that they supply, supply. And as probably people have seen and often discussed, that there's a lot of registers and things that you can use or need to use to make use of the peripherals that are available, and fathoming your way through the reference manual to work out exactly what you need to do to get a certain function working can be quite complex. And the usual approach has been what you see on the web, where people follow the C style of things, where you've got names for all the registers, names for all the bits, and you write a definition which manipulates those bits, and you end up with hundreds or thousands of words to cover a fair range of peripheral devices. And I mean, I've been just picked up the code that MPE had supplied as a starting point, and generally used that, which is of a similar style. Let me see somewhere. I got in. I did make some notes somewhere, but let me see. There was quite a good example here somewhere. Let me look. No, clock, I think it is. No, sorry about that. I don't see. I thought I had it here somewhere. anyway, I can show you the way things are usually defined. In Agon gives you two ways of viewing things, which is quite handy. So basically, chapters are standard files, and they are divided into sections, and in the sections you have definitions, units. So if I select memory there, I've got notes what that is about, and then various memory areas of the memory map are defined as equates. It's a constant in the cross compiler. That number, I think, is standard on the ARM processors. That will be on every variant of the ARM processor you come across. The STM has a region of EEPROM and some other options for users. And then a RAM usually starts at that address. And here defined the buses, ARM peripheral bus, ARM peripheral bus B1, APB2, host bus. These are, I think, pretty well defined again by ARM. So here's a good starting point. Then each of these buses has various peripherals available. So host bus has a DMA, and you've got a list of all the registers in that bus, in that peripheral. The reset and clock control is probably where you need to start, because that controls each peripheral with a enable bit for the various functions, and they're all embedded in these registers. So you can see a list of those. They have a name sort of defined by STM and in the reference manual. So you've got the reference there. This was the basically original code convention that MPE used, where they isn't an underscore in the name, which was quite handy, because if I see this code, I know it's sort of using the previous coding method, but I've now adopted the STM format, which has an underscore in the register name, like here. CC. Here, like this. So if I'm coding using the new scheme, at least I don't get confused with sort of duplicate names. All the new code uses the new name format, which matches exactly the STM standard in the reference manuals. So I've got to thinking about this some time back, having had a break from it. I thought, this seems to be a bit clunky, and there must be a better way of doing this in Forth, handling all this stuff, because you can look at one of these registers and you can see the register's got, you know, anything from 1 to 32 bits to do something. That was not much in, well, their own, I've only here defined the bits that I'm using in this particular program. So the solution, of course, was the magic creates does pair, which is one of the most powerful parts of Forth I found. So I looked at what you need to do, and I mean, you can look at the code that everybody does, and basically it is a register name and a bit definition, which you have to then set or clear or read. And all the words that people write all do that. So you have a straightforward, simple thing that you need to do, which is 2 lines of standard Forth. So a reg bit needs to know the base address of the module, the peripheral, which is specified, and the offset into that register set, and the bit number that you're dealing with. So create lays down the bit number, adds the offset to the base, and lays that down, which gives you the register address that you need. And when you run it, it returns those 2. And of course, the nice thing about doing this is you can then use the name, the STM, call this bit in the register, in the reference manual. Like, I was hoping I could go to a different screen where I've got my other things showing, but how do I change this other screen? You can't, these paused. How do I switch to this screen? Anyway, I can't, but, well, I maybe can, but haven't found it out. I tend to
I've not found a way.
Multiple desktops, very handy. But,
you have to unshare and reshare the other screen.
Switch to the other screen, do I? So I'm going to click on something. I've got to stop share. Yeah, is that it? Resume share. No, no. And then I've got to select it again, have I? Share screen. Where's it gone? Oh, here, reference manual. That one. Is that square sharing? Yeah.
Yep.
I've got actually 2 manuals showing on my screen, but it's only showing you 1, I think, is it? Or 2. Can you see? No, it's sharing me, is it? Not. I don't understand. If I click on that one, you are screen sharing. Who can see what? Can you see a part of the reference manual with highlights?
Yes.
Yes.
Oh, you can see that. I can see myself in the other screen. Yeah, so you can see the bits are named and they're consistent across the function. They are consistent, so they are unique names. So we now have a method of using the names that STM have used, and it doesn't take any bulk of code to make use of it. Can I go back to my other screen? Oh dear. Here, this one. Where do I? Oh. If I move Zoom onto the screen I want to share, does that work? Oh, I should have. Desktop. That one. Let's see what. Let me share. I want to go back to this one. Hold Shift to select multiple windows. Ah, let me do that. Share. Ah, that's better. So I think you got back to a whole on screen. Is that okay? Where I was, I hope. It's got a green border around it. Yeah. Yeah. So we can look at the various things I've got here, and I end up with a name which does what I want. Enables port A, or enables the DMA peripheral, or enables the USART1. So at the end, we end up with something like, where are we? ADC config. ADC config. So to configure the ADC module peripheral, all we need are the name of the bit that you need to set, and that's the code. Again, there's nothing more needed. You're not specifying a base address, adding an offset, looking up a bit number. That is all built in via the creates does into ADC enable. There, so if I click on that, so it tells me, oh, hold on, tells me it's there where I've clicked on it, and it tells me it's in that register, a PB2 enable register, and it's bit 9. So we end up with something which handles so much of the complexity. All you need to do is to go through and the list of the registers, a line of code for the bits you're interested in. And then we can look at again in the DMA section, we can then ADC DMA enable is select that bit, which tells us is there. We can check this back against the reference manual that we've not misread anything. Because the problem is not every chip matches another one in the family. The functions are different. They've even remapped some of the registers. So from one variant of the chip to another, you would have to redefine, or reallocate the correct bits in your code. But that's fairly straightforward, and it's obviously you can check this. You work from the reference manual to do it anyway. But probably 90% things don't get moved around. But over time, things can get a bit confusing, and obviously you've got to read the right manual for the chip you're using. So again, we can look at, this is the DMA configuration. To run the DMA, you need to run a timer, which triggers the ADC operation, and then that map copies ADC outputs from different channels into a buffer, which wherever you defined it. So we've got a DMA buffer. So that takes a couple of addresses, the source in the ADC, from the ADC data register, and from the array you've defined in position, and DMA address, you need to address the, you need to select the right DMA channel, which is channel 1, and the DMA module. This chip only has one, but some have two different modules. So you have a DMA1 and a DMA2. And that is all the code you need. You don't need lots of fixed addresses, which is the method that you'll see used by Macrisp and volksForth, but so you end up with a huge file of definitions, which is not easy to manage. This, we've got the solution here. If it's another function on another DMA controller, a different channel, we just change the numbers here. A one word definition. So, and obviously it's very easy to interactively test because you haven't got to do a lot of typing. You straight away can see here what's typically there's a setting up the actual DMA. You have to specify the size of the source and the size of the destination, whether the memory increments, whether it's a circular buffer, all nice and easy to read. And of course, because there are typically 7 channels available in the, you'll see that most people address these with a DMA channel 1, DMA channel 2, DMA, etc., etc. But a simple calculation does that for you. You don't need to define things which are offset by 20 bytes, 5 cells. You can calculate it from a base. So we've removed dozens of names in dozens of definitions with a simple one-liner. So I think this probably covers the whole concept. As you could see, there are, where are we? This one. Something here, define. So there are sort of 2 variants. If you've got one module, you can compile its base address into the definition of the word. Some modules like UARTs, obviously it could be 2 or 3. So you don't want you want to specify the particular module you're dealing with at runtime. So you simply you provide the the module USART1 or USART2 and the bit function in the code. So you can look at something like USART1 setup. Yeah. So those are the UARTs there on this particular chip. There are 3 USART1, 2 and a low power. This is often available on other variants as USART3, but this is a particularly low powered peripheral designed for use when you want to wake up the processor from sleep. Obviously, it can be virtually active in sleep mode without causing much power consumption. So we can look at any of these and see which bits are which. So the UE bit enables the chip, the peripheral, and you've got receive enable, transmit enable, receive, interrupt, the other bits, M0 and M1 are the bits to change the data width. And DMA receive and transmit are on in this register. Overrun disable, interrupts status, RxNE, receive not empty. So if I click on that, you can see where we've used that definition. So key function obviously is wait until that bit is set, or wait while it is 0. When it is set, we just read from the data register. And that we then look at USART1 key. It's the same definition with the same word name, RxNE, but referring to USART1. And there's no one there, USART2. Somewhere I did have on here, I should have made a marker for it. There was code for configuring, but US2 in it. So this is the new version of initializing a USART channel. So that's enabling that whole USART from the main reset and clock control. There we are, RCC, APBR, APV1. Oh, here, sorry, USART2 enable, bit 17. So in Holon, this is the word that's the unit, the name. So all the bits in that register are available as a list here. You can still select. It's not used. I do so.
Michael, I think we are moving slowly into the end of this presentation, so we can follow with the next. If you can round up the whole.
Yeah, fine, that's okay. Has anybody got some questions? Hopefully I've shown the potential, and hopefully people will tackle some of the peripheral usage, things like the counter encoders.
I think Atle and probably Christian have a question.
Yeah, I did send Christian some code, but I don't think you had a chance to delve into it too much yet.
I just got one question. Can we download all of this?
Yeah, I should say so. I did send Wolf this as a zip, which gives you. It's not a complete application. It is just a whole I threw together for this purpose. But the various bits are used in proper complete.
Yeah, no, it's okay, because the thing about this is it's such a beautiful way to raise the abstraction level.
Yes.
So it doesn't matter if it's complete or not. It gives a beautiful framework for doing it.
Yes, that was my idea. Obviously, I could. I've got systems which I'm converting. I've used this in a couple of recent projects, but there's bits of old code which I will go through and replace.
Yeah, it's excellent. Thank you.
Okay, I have got a live system here, but changing windows is not so easy, I think. I could.
Yes, Christian, go ahead.
Where do I go?
You are muted. You are muted. Your microphone. Christian, we can't hear you.
I missed a bit of the presentation. I was outside with my wife having a soup. I saw that most of the register name in there are pretty well the same as what I saw on a blue pill.
Yes. I did have a screen with to compare the various, section of the manuals, and they've got the same name, but they've moved. But that doesn't matter as long as you've got the name.
Which type of processor was it intended for?
Well, just the whole family, because as you say, they are very consistent in all the names of bits are unique. So
okay. Sometime, depending on the microprocessor, I'll have the same field, but maybe sometime in a different location.
Yes, that's right.
I have
the bit number changes, the register offset changes. They change the I/O ports from the F series onto a completely different I/O bus on the L series. But if you just change the base address of the module, you use the bus name, the code all works.
Okay, so basically only the address, the register address to be changed, or the base address.
Yeah. If those are in the beginning of the code, and that's the job done.
I could have used this a few months ago. I was helping a friend to figure out how to debug some of his problem on the CNC.
Yeah.
And well, I thought that FPGA was a good way to debug. So it was the hardware he couldn't get to work. And testing with FPGA, we could get it to work properly. And this could have helped a lot. So next time I'll have your tool.
Yeah. I can send you this updated version with more detail in it. So you can
So
see
thanks a lot for creating this.
yeah, I've got I think you'll see this terminal screen.
Yeah.
Yeah. Let me get rid of that. Yeah. Ooh. So on here, I can just do things like USART 1, USART enable, right? That's going to address that. .s will show me it's bit 0 at that address. And if I do bit fetch print, it says it's enabled 1.
Yeah.
If I say ADC and because there's only one ADC, all I need is the name of the bit. Yeah, .s is the 9th bit at that address. Bit fetch. Oh, sorry, done it. ADC enable bit fetch print. 9th bit 512.
Yeah, I had to do.
And I can turn that off if I want to now with ADC enable, ADCN bit clear. Done. Didn't have to type more than about 6 characters.
Yeah. Excellent presentation, Michael. Wonderful.
Okay then, good.
And then we continue with the wonderful FORCE 2020 meeting. And the next participant is Howerd Oakford with Colorforth, or I think something with his Inventio site.
Yeah, that's right. What I'm going to do first, because I know it's getting late and I'm going to have to go soon anyway, but I'll keep it as quick as I can. First, I'm putting some links in the chat. It's a link to the PDF file I'm about to present. And I'm now going to share my screen. And hopefully, this one, I think. Okay, can you all see a nice PDF file? No.
Yes.
Oh, I can.
Yes. Oh, now it's there.
Yes.
Oh, it just takes time. That's what confuses the issue. Right. Okay. All right. So this is entitled Colorforth, the Next Generation. And I don't want to go into too much detail here. You can read the PDF, but I want to explain. I started out writing Colorforth. What is it for? I was asked, I think the last time I came to one of these group meetings some months ago, I was asked, what is Colorforth for? Why am I doing it? And I tried to write an answer. And then as I was doing it, an idea came into my head. And I thought, well, I just have to do this. And this is actually why I like Colorforth. Because even when you think you've looked into every corner, you haven't. And there's always new things coming up. So I want to talk about this. So what I realized I need more colors. To be precise, I need one more bit. The current Colorforth system, which is exactly the same as Chuck's original version from 2001, uses a token format with, hang on, just get rid of this. I'm just trying to get my screen into some sort of order here so I can see what I'm doing. Right. These are the colors. So you have a 4-bit field in each Colorforth 32-bit token. The 4 bits represent the colors, and then there's the remaining 28 bits are like compressed, like a little zip file of the name. You can get up to 7 characters into 28 bits because 8 of the characters are only 4 bits. And the others are 5 or 6 bits or more bits. So it depends which characters, but you can get quite a lot in there. Now, the reason I need one more bit is because magenta variables are these weird things that store the information, the data of the variable into the source code block. If you don't know what that's about, then there's other papers I've done about this, but you can see it in a hex dump here. The C here is hex C, meaning the color magenta, and the value of the variable is stored in this next cell here. Okay, so this clashes with the concept of extension tokens, because what you're trying to do here is you're trying to deal with one 32-bit Colorforth token at a time. You're always focusing on just one. And within that token, I can't seem to highlight on this PDF, but I don't know if, can you see my cursor on the screen?
No.
So,
Yeah, yes.
You can, good, okay. So you can see where I'm pointing here. This is one Colorforth token. This is 32 bits. You've got 91D0C, 6C. Up to those bits, those are the 28 top bits, which represent compressed color, like so. And the 9 indicates a white lowercase text. Then on the next cell, you've got a color of 0, if you like, which is the extension color. And so what that says is don't change color to the color marked here, but continue and remove the space that was added for the first token. So if you look at what is shown here, it looks like this. So the color F and then the auth are joined up here. Normally, after every token is displayed, there is a space. Colorforth doesn't have a space character. This is one of the interesting features. Anyway, so you can, if you go through here, this is just a hex dump. This is the address, and this is block 64, which is the start block of the Colorforth source. So this is how it works, and this works very well. It means that you can have longer words than can fit into your 28 bits, even when it's compressed. So you can see that happening again here, that the CF2023, you can only fit CF20 in here, even though there's a gap there, but you can't fit the 2 and the 3 here. So that needs an extension token. But this is inconsistent with the way magenta variables work, because if you, the next token here is the information contained in the variable. What that means, if you try to define a magenta variable whose name is too long, as I'm doing here, it's called long name. You can't fit long name into one token. What it tries to do is to put an extension token here. So you can see I got as far as long na, and then the M and E for the long name had to be put into an extension token with a extension color of 0. So normally that would work, but the problem is that this location here is defined as the storage location for this magenta variable. So what happens if you do that is it thinks I've defined a variable called longer with a value of this, and you'll see that this -197 blah 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 is the same as the hexadecimal 8A, which is this, which is what I was, the name extension. So you've got a fundamental architectural problem here, that you cannot have extension tokens in that form together with magenta variables, because you cannot tell if the name field, if you like, is a variable length. So normally this would be long name, and this would be, it'd be a 2 token name string, if you like. You can't tell when the name has finished, and you should start to consider that to be the location where the value of the variable is put. I mean, it works now because we simply are saying you cannot have magenta variable names that don't fit into one 32-bit value. So how to solve this? And it occurred to me that what you really need to do is you need to have an extension bit. So every token, rather than saying I am a colored token or I am an extension token with a color of 0, you add a bit onto every one of them. And then you can mark, this is the beginning of the name, this is continuation of the name, continuation of the name. And when you flip the bit, that's the end of the name. So you're then like encapsulating a name string, which can have more than one 32-bit tokens in it. And you know where it begins, you know where it ends. Okay, so if I take a bit out of the 28 bits that we had, there's certain words that won't fit in there anymore. For example, R-shift. R-shift, this is the RSH. You can't map the bits cleanly to the characters because they have varying bit lengths. But the problem is the 1 here, which is occupying bit 4 in here. This, if you the rightmost end is the lowest bit. So 9 is 1001, and the next nibble up, 4 bits up, means it's 0001, 1009. So this name, unfortunately, the T is occupying the 5th bit, bit 4. So if I were to give myself a whole extra bit in the color token, I could have 32 colors rather than 16, or I could use that bit to say I'm a start of a string, or I'm a continuation of a string, I'm at the end of a string, whichever. I haven't quite decided how to encode that yet. Then I cannot have the name R-shift in a single token anymore. So if I can just change my screens, I wonder if I can do that. I want to go to a SwiftForth application. Where is it? I have to find it here. I will go to this one. This is the wrong one. I'll change it. I want to close that. Oh, okay. It's not easy with this screen sharing, is it? I'm trying to find this is the one I want. So I need to, can you see some colorful forth now? Or do I have to share again? Share again. It can't be that difficult. Here it is. I want to share that screen. Right. Okay. Can you all see that now? So what this is a SwiftForth application that I wrote called Colorforth Scan, which I use to deal with Colorforth source code on in a normal Windows environment. So this is taking the code from the Colorforth system and printing it out in a conventional Forth form, so it becomes human readable and so on. And okay, now what you'll see on here, you've got these inverted bar greater than tags here. So I went through and I said, if a fourth word here is occupying actually the extra 4 bits, then I will mark that. So very hard to read that, but that word is plus through and it's yellow, and that is if you take away bits from the name field, you cannot fit it in anymore. Likewise, you can't fit in rand q, pause, calculator hertz, block, all sorts of words. So I went through and said, well, what words, what will I lose if I do this? You cannot encode query dupe anymore in this. Okay, so this is a very helpful program, and that tells me how much work I have to do. I have to go through every token in the entire Colorforth system, which is 256 blocks. I'll do this with the program, obviously, and check if it fits. If not, then I have to make it fit and then add an extension for it or change its name. So this is, let me just run it again. So this is what it looks like when it's calculating it. I think it looks quite nice, but you probably can't see much of it going on there. So that's going through every block in the Colorforth system. Right, now I want to go back to the other one when it's finished, maybe. Yeah. Right, so I'm now going to share again and go back to the PDF, hopefully. Okay, are we back? That seems quite painless. Right, so then I said, okay, so I absolutely need one more bit. You cannot have a variable length magenta variable name if it's always got to be in the next token address following the name, because you cannot tell when the name ends. But if you add a bit, if you have an extension bit, then you can tell when the name ends. Okay, but why stop there? By taking one more bit, we can have 2 bits for what I'm calling structure. And this encoded the 4 possible values of these 2 bits are carry on, just kind of like just do what you were doing. Drop down a level, jump up a level, or end of sequence. Now, using this, I believe you can encode structured data like JSON and XML files and Holon structures, maybe. I've also been a fan of Holon for a long time. And you need some way of putting structure into that. I'll just stroll down and talk a bit more about that. So say you want to store a JSON file. This is one I picked up from the internet. There is structure that this is the name of a class or whatever, and these are elements in that class or some such. I don't know what the exact terms are for JSON files, but you have more than one of these. So using these 2 bits here, I believe you can encode structure. This is theory at the moment. I haven't implemented this. I haven't shown that it works, but I'm reasonably confident it will work. So what you do is the on one, it just means carry on, don't do anything up or down. So the first thing here is you're trying to encode the name of the class name student, which is, you can't fit all of that into one Colorforth token. So the open square bracket, closed square bracket represents one 32-bit Colorforth token. And the on field means those 2 bits are saying carry on. And then this is the 24 bits I'm saying now, because I want to take an extra 4 bits. So you then have an end flag here for the end. So at this point, you know that you've got the name student, which is the combination of these 2. Then you need to jump down to give the ID, because the ID is in the next indentation, in the next kind of level down. I'm saying down, maybe I should say to the right to correspond to the way it's indented. So you can put the name ID in there, and that should be highlighted, but it's not, sorry, typo. And then you go up. You say, well, I'm ending the ID section now. So I go down into ID, then give it a value. Then I come up, so the value is 1 there. And then you go down, give it a name, up when you finish the name, etc. So you can encrypt structure in that, I believe. I'll see how that works. I need to import and export these things and see whether it really does work. Then I want to take a couple more bits. So I want to add a version control to Colorforth, because my version control at the moment, it consists of taking the file from the box emulation system and archiving it as a zip file. So it doesn't give me anything. It works, and if my computer crashes, or I want to go back to an old archive, I unzip it and it all works. But what I want to do is to have 2 versions of Colorforth code on my system at the same time, from me and from somebody else, and compare them. I mean, it seems quite normal. This is obviously, when I say version control, you're probably thinking of things like Git and SVN and things, which are fantastic, of course, but I'm not talking about that really. I'm talking about version control of one Colorforth token compared to some other source that has a different version of it. So this is the Colorforth style of version control. Very, very simple. So what you do is you have, again, 2 bits for this, and they define that this is a token that both me and my colleague Bob have. He's somebody working on something somewhere else on the internet. Then if it's got this flag, it's saying this is only me. And if it's this flag, it's only him, the other version. And this flag is used to say, well, I used to have this, but I don't want it anymore. And I'll explain why you flag it up as a blank. So just to say, this is, where are we now? So yeah, so this, what I want to do is I want to change the Colorforth token format so that I still have a 4-bit color. That means I don't have to change anything that works now, but I take 4 bits from the name. So there's only 24 bits now for the name, means only 6 characters, 1 less possible. And this has some advantages. It means that the color and metadata are 1 byte and the name fields are 3 bytes. And this makes it easier to map it to ASCII or UTF-8 if I want to do that later. Reducing the number of bits for the name means that more tokens will require extension tokens because they don't fit anymore. And this will increase the code size. And what I want to do to compensate for that is I want to not do what I'm currently doing, or Chuck currently did, and I haven't changed, that each Colorforth token in the word list is compared only with the first token. It ignores extension tokens in the word list. So if you've got a value, a word, my value 1, and then my value 2, probably the my val is in the first token and the UE2 or UE1 is in the next token. But in terms of dictionary search, they're the same. So they will overwrite each other. So when you define my value 2, it will actually come back. If you search for it, it'll find my value 1 first, or the other way around. It'll find 1 and it'll overwrite the other. So adding an extension bit also means that when I compile something, I can say, is this something that has an extension? Should I look further for doing the comparison? So given that most of the Forth words, the Colorforth words in Colorforth are quite short because they come from Chuck's original thing and he just loved short names, it won't have that much impact. There'll obviously be a test for the bits to say that I'm not the end of that name and I have to do some more work. So there will be a slight overhead there, but it shouldn't be too much. Okay, so if I go in more detail about version control, the point is here, Bob and I want to work on our latest Colorforth project. So the tokens are marked as either, my version or other versions. So what I would do is I would have my blocks in 256 to 511 on my machine, and Bob's other tokens are in blocks 1000, 256 to 1000, 511. So we start off with the same code, and I edit the name of a token. There's only certain things you can do. You can edit a token, you can insert a token, or you can delete a token. So say I'm editing the name of a token from rshift to rshift because I can't fit it anymore, and then I want to do this. I mark the original token as other, and I insert my edited token marked with my. So they're both in the block on my system in my code base. There are now 2 tokens in there, one with the word rshift in it and one with rshift without the T. One marked as other, Bob's or earlier or whatever, and one marked as my current edited one. And the editor would be changed so that it will look at the flags, the version control flags, and say, well, I'm only going to output ones that are either both versions, that's this one here, or my version. And then if you press F2, it goes to both versions and the other version. So what would happen is that as you pressed F2, the T would appear and then vanish. So you could hold your finger on it and you'd see the T flash. So you could see exactly what had changed. If I insert a token into there, I'm putting a new token in. But what I would do as well, when I put my new token in, I would add the same token marked as deleted. That's for the other token. This means that when I press F2, I'll alternate between my tokens that has the inserted token in it and the other tokens which have a token inserted in it that you don't see. So the new token that I've just inserted would flash. But the point of this is that all the tokens being displayed after my newly inserted token don't shift because there is a token there, it's a blank one. And by the way, don't worry if this throws your brain. This is taking me maybe 15 years to work out. So I don't even know if it's going to work. So similarly, if you want to delete a token that the other guy has, I don't want it anymore, it's in his, then I just mark it as deleted. So when I toggle between my and his views, I see the blank where it was. It's not removed apparently, but it's blanked. So again, you see it flashed as something that's not there anymore. At some point, we want to export it. I want to show Bob what I've done and vice versa. So the my and other code can be compared, and we choose which one we want. You have a keep mine for each token. We say, I want mine, I want his. Then the one we choose will be replaced by the both, and then the tokens marked as deleted can actually be taken out and the blocks can be exported. At some point, you probably want to take a sort of history of this and file it somewhere in a file somewhere. Okay, I have no idea whether anyone knows what I'm talking about here. But I think what I've tried to do here is I've tried to write down at least 3 ideas that I've been thinking about for a very long time, and a new format that, let me try if I can find the format thing again, going from a 4-bit color to a 28-bit Shannon-Fano compressed name to a 4-bit color, stealing 4 of the bits from the name, making the name shorter. This means fiddling around with the current source code with a program to convert, which is not easy, but it's, you know, I'm allocating a few weekends for that. And it gives me a new feature of the extension bit, which means that you've decoupled the name, the length of a name. It means that you can encode a string, which is also something I've been trying to do, because currently you just don't have strings in Colorforth. I think with that, I will stop. As I said, I've put the links to the PDF and my Colorforth webpage in the chat, and that's it. So I'm hoping to get this done for CF 2024, which is only, where are we now? August, only about 4 or 5 months away. Any questions?
A comment, and well, yeah, I love the idea with the structure. That's actually kind of a neat direction to take the encoding. I wondered something I've noticed the same problem of sort of the limitations of the encoding. Had you considered placing the one thing I've often wondered is if you put the extension, if the extension came first, then you would see a series of extensions, and then sort of the word with the color labeling, that would sort of eliminate the problem of the next item in the stream being ambiguous or more complexity in trying to find the next cell.
I couldn't quite hear all of what you said, but I'm assuming that what you're saying is exactly what I intend to do. That is that the you use the extension bit like inverted to say, if you put a token in there with the extension bit 0, then it's saying that I'm only 1 token long. And if you put a 1 in there, then I'm saying that I'm not the end. So look at the next one. And if that one's got a 1, you look at the next one. And if that one's 0, then that's the end. So this is giving
subtly different. What I meant was that with Chuck's existing encoding, I've often wondered if it would have been better to have the extension be a prefix, and so you have a series of prefixes until you get to the word the one that has a non-zero tag. But certainly you get more flexibility. Yeah. Certainly you get more flexibility with the using additional bits instead.
Yeah, absolutely. I mean, I did think about using a prefix, but then you have to say you're changing the state of the Colorforth system to say I've entered a Colorforth string state, and then I'm going to wait for a what do you call it, a postfix or something, a flag at the end. It's a bit like HTLC, where you begin what's the word? I'm trying to say block, a kind of sequence of characters. You begin it with a flag character that is not ever going to be included as part of the content because you escape that flag character. And I thought about doing this, and it's not consistent with the Colorforth focus on just the 32 bits, because by doing it this way, it's expensive in terms of the whole bit. It's one 30-second part of everything is now kind of lost, if you like, or that's the cost of it. But it means that you can still consider every 32-bit Colorforth token as an isolated entity. It's not dependent on any state in any other system. And I think this is something I'm going to hang on to as long as I can, unless there's some other reason for it. Obviously, viewing the source has to have some kind of state that we resonate and see what the changes are. Okay, is that okay, Brad? Did I answer your question there? But
yes, you did.
Thanks. Okay.
And definitely the structure that's an interesting direction to take things.
Yeah,
and the version control.
Yeah, yes. Well, I've been trying to put these in, trying to force them in. I thought, well, if I'm going to steal a bit from the name field to give myself more flexibility in the color field, then let's do it properly. Let's take 8 bits rather than 4. Gives me these 2-bit fields that I can do really interesting things with, and I'm still self-contained within the 32 bits, and it doesn't have that much of an impact on the code size, I don't think. I mean, I would say about 1 in 15 or more token names that currently fit into 1 token won't fit anymore. So you'll add 5% to the code size or something, and a bit of time.
Howard.
Yeah.
Okay. That was wonderful. Again, thank you so much.
Thank you, Peter. I hope people understood it. It's kind of obscure, but if you take the PDF file and a cup of coffee and just sit down for a while, it's if you think you don't understand something, it's because you're trying to make it more complicated than it is. It's actually very simple. It is actual bits. It's just there is nothing else. Okay, guys, thank you.
We are very happy every time you join us and show us the great things you produce with Colorforth.
I hope I can actually make this one work, or these 2 concepts work.
Excellent.
We shall see.
Then we need to move on, gentlemen, to the last presentation of the meeting with Klaus Schleissiek from Hamburg. It's the microcore workshop.
I unmute myself and welcome to the workshop. I will start sharing my screen for a second. Oh. Okay. Okay, so I have prepared some things. Jason did ask for how do you add registers to the design. I will come to that later. First of all, the good news is the getting started.pdf is now available on GitHub for the Cyclone for board. And that should kind of help you to get the hello world experience with microcore if you have the proper board. It also contains all the all the URLs for the board itself and for all the software pieces that are necessary. Since my last workshop, actually, new instructions crept in. And a new way, which is even more important, a new way of how to deal with, let's call it luxury instructions. I have made in the architecture package file, I have made a long list of with plus st definitions. I'll show you how this looks like. There they are. There are all kinds of with index, with p-loop. So these are all the instructions which previously had been activated when you said with extensions or with extensions is true, and that was most of the time you needed one or two of those luxury instructions, and then you got all of them. And now you can go selectively. So in the current implementation, I have set 3 additional instructions to true, which are the index in a do loop, the plus loop, which is new, and then a fetch instruction where you don't have to drop the address after doing the fetch. It does this automatically. Okay, so, oops. So this is this with plus store rigmarole. Now, if you have not allowed to an instruction for plus store, so with plus store is set to false, then in the force library, you have to do a colon definition for the plus store. And then there is one difficulty that arose, and that is that you do a fetch store type of instruction where you do a fetch, you do something to the value, and then you store it back. And in between, there are no interrupts allowed, because the plus store instruction is one of those that can be used for interrupts to communicate with tasks that may start to run or whatever you want to do. And so I had to temporarily disable interrupts, which is this bracket DI word. Oops. The bracket DI word. Then then the interrupts are disabled, and then you do your fetch and at the end to the value, and then a swap store will store the new value back, and then you say DI closing bracket. Now, why could I not only say disable interrupt, enable interrupt? That is very simple. Because plus store may be used inside of a definition that has inside an interrupt itself. And the interrupt itself, by definition, has the interrupts disabled again. So if I would say enable interrupt at this point, then all of a sudden I would enable interrupts, although if all went well, they should stay at being disabled. And so these brackets, sort of bracket DI and DI bracket, take care of this situation. And the way I do it is I push the current status register bits on the return stack. So while I do the fetch plus swap store, there is this old status that was valid up to this point on the return stack, and then the DI bracket takes it off, looks at the return stack, and restores the interrupt enable bit. And so that makes an interrupt safe plus store in a very easy way. And since these sequences of disabled interrupts, I mean, they increase the interrupt latency of the entire system, because when an interrupt occurs, it may be at the very beginning of the sequence, and then the interrupt will not be recognized until after the DI bracket. And so I thought these must be fast, and so I promoted them to actual instructions, which are single cycle instructions. Another thing I finally did, I don't even remember why, but I felt the need for a plus loop. Yeah, because I started with byte addressing, and then all of a sudden, if I run a loop on addresses, I have to increase the loop count by the number of cells and not only by one. And so I have the same situation. I either have a special instruction with p-loop, which is a one-cycle instruction. And if I do not have p-loop, I do have to do this in high level. And you see this is quite a lot of work in order to get it right, because the plus loop depends on whether my increment is positive or negative. So I have to test the increment, and then depending on whether it was negative or positive, I XOR it with a carry, and if the result is still set, then what I actually do is my plus loop computes a new loop index. So if the loop index had be at, let's say, 3, and I do a -4, and I do a 4 plus loop, then the result of this, if I do not check for overflow, let's call it, would be a -1, and the loop would never stop. And so what this expression does, the XOR produces either a true, which is -1, or a false, which is 0. And then the end takes care of, if there was an overflow, then I mask it away, the result, and set it at 0. So, and given this word, here is how plus loop works. It does the parent plus loop, adjusts or computes a new loop index, and then the next goes ahead as usual with the down counting loops. More complex things, what I've done. Running a brute force division multiply test on a 10-bit architecture. And this is now also on GitHub. So if you are curious, you can take a look at it. I was able to cramp a simple version of a stripped down version of the multitasker, plus the routine that is necessary to do the division multiply checking in under 1024 instructions, which means it would fit into a 10-bit architecture. And in a 10-bit architecture, the brute force division multiply test only takes 3.5 hours and not days or weeks or months. So in 3.5 hours, every possible case, and every possible case means I have a 20-bit dividend and a 10-bit divisor, and I go through all bit combinations that are possible. And it works nicely, and because of this, I'm sure that my division and my multiplication works correctly. And also what I did change in the microcore code for the board is I implemented a 250 microsecond interrupt that always runs in the background constantly and interfering whatever is happening in the foreground, so that if there would be any interference with the interrupt and the foreground process, I would quickly take note of it, because the system crashes or does wondrous things. And so it is always a good idea to have regular interrupt running in the background. So these are the new things. As far as interrupt processing is concerned, at a later time, I think we will come to that, how you define a new interrupt source and how you program the interrupt source. And today I would like to concentrate on adding registers and interfaces. So any questions up to this point? That doesn't seem to be the case. So I move on. In general, I have described on how to add registers to the design in the mycore.pdf. And so this is one page, and it gives you a step-by-step procedure of what you have to do if you want to create a new register, and how you can in the VHDL code, it is possible to find that either a store or a fetch has been applied to this new register. So this is something you can read to understand of what is happening here. And basically, we are not talking about registers. I mean, usually we want to do something with a register. And I have picked two examples of interfaces I have done, which is a DAC converter. This I have done while I was working in the space industry. So these are radiation safe DAC 128S101, I think that is Texas Instruments, and ADC 128S102, also TI radiation safe. So but they are constituents for a broad number of chips which are not radiation safe, which are commercial off-the-shelf chips, and they operate the same. Basically, these are chips that are connected to an SPI bus. Jason asked me, so how would you, for instance, handle the SPI bus? And my answer was, well, I do not explicitly implement an SPI bus. Instead, because I'm doing a whole interface in VHDL, I don't have to program the interface on the SPI level. The SPI is just something that automatically works in the background, and I'm more concentrating on simplifying the handling of the peripheral interface. And in the case of the DAC, all you have to do on the fourth level is you put a value on the stack, you say DAC, so DAC is a register. You say DAC store, and that's all. I mean, you don't have to look at status registers nor anything else. You just do the DAC store, and that feeds the next value into the DAC. And as far as the ADC is concerned, The same holds true. It is more complicated though, because this is an ADC with an 8-channel multiplexer in front of it. And so this is a two-step procedure. I store the channel number in the ADC register, and that starts the conversion of the value of this channel. And once it's finished, I do an ADC fetch and return, which returns the sample. The point is, after a while, the sample becomes available, and usually what you do in between the store and the ADC fetch is you have to go through a loop, check a bit of the status register, whether it is true or false, depending on whether the ADC is ready or is still operating. In microcore, we have the pause input. So if you properly use the pause mechanism, then you don't have to do all this status bit stuff. You even don't necessarily need the status register itself. All you need is a bit in the flag register that tells us the ADC is still busy or the ADC is finished, and that is sufficient for, and with the proper logic around it, producing a pause signal. And as a result, all you have to do with the ADC is you store a channel number in the ADC and you fetch the result, and you don't have to wait for anything. Because automatically the ADC fetch will raise a pause if the ADC is not yet finished and let another task run, perhaps. And at some point later on, coming back to the same code, and we'll try again. And eventually the ADC will be finished and you will get the result. So to get you an impression on how complex the interface code for the DEC 128S11 is, here is the actual VHDL code. And you see this is not much. And so to show you of how this works, we have a DAC chip select. So this is this output signal and then the DAC data in. So this is the name on the peripheral chip side. So as far as microcore is concerned, this is of course an output that goes into the peripheral chip.
Klaus, can we see your screen larger, because I can't read your text?
You can't read this text, okay. No. I can make it larger.
If you make full screen of your notepad.
Yeah, but then I have to switch back and forth with, I think I will just increase the.
No, make it larger, because we see only 50% of your screen. Exactly. Yes.
Now,
larger.
do you see it now?
We see only 50%. The rest is a big red block.
Yeah. This is this red area here, and then we have. Well, I mean, another thing I could do is this, but the characters will not get larger. So, is this readable now? Peter?
Yes, no, not very well. Not really very well. The problem is, since we are recording this for the future, people will not read it.
Oh,
well, I can read it fine.
Can you read it? Okay.
Yeah.
Then let it be. Let it so.
Yeah. So, where was I? So the chip select, or let's first go through the signals. So I have a shifter register, which I call shifter, which is something of 16 bits because a DAC needs 16 bits for one transaction. And I have a counter that counts from 16 down to 0. So I kind of count the bits. And whenever the duck counter is at 0, then the interface doesn't do anything. And the chip select, so if the duck counter is 0, then the chip select goes to 0. And whenever it is any other value, the chip select is true and the peripheral chip is activated, the DAC is activated. And so here we can see how this works. So for one thing, there is the S clock, which is the SPI clock. So this is the clock speed of the SPI interface, which probably is very different from the clock that is used for microcore itself. So I only do something if S clock is 1. And then if the duck counter is at 0, I fall into the else loop. And so if write equals 1, which means I did a DAC store on the software level. So, and the write is an input, and the write is actually triggered by the VHDL code that checks. Oh no, I'm saying stupid things. So the write is triggered by the store. The write is triggered by the store, in which case I load the shifter with 4 leading zeros and the actual data, which I also handed over at this point. And the duck counter is set to 16. And so in the next cycle, when S clock goes 1 again, the duck counter is not equals 0. And I shift the shifter by 1 position to the left, and I decrease the duck counter, and then I'm done until the next S clock signal. And the duck DN, which is just a single bit, the input line into the duck is the bit 15 of the shifter, which starts at 0. And this is basically it. And then I have a clause for what the interface does on reset. Of course, it is important to set the shifter position bit 15 at 0. So I just place a 0 on the duck DN line. And the duck counter is 0, so I will not do anything here. I will just wait for the first write signal to appear. So any questions at this point? To put it another way, instead of having a general purpose SPI interface, which was just take care of the shifting and perhaps not even the counting, and then having to build a lot of other things on top in Forth high level, I did all this nitty-gritty stuff in VHDL, and as you can see, this is not much work. And it is much, much easier than building a general purpose SPI interface where you can say many things like whether the chip select signal is positive or negative logic, and how you initialize the shifter, and what speed it should run on. This is all not necessary because microcore is written in VHDL. If you do a microcore design, you are already doing the HDL on the FPGA, so you don't need a general purpose SPI interface. I mean, the SPI part of an interface is just hidden in the interface code itself and parameterized at the point where you really need it. Like the same thing is true for the umbilical UART that does the communication between the target board and the host computer. This also has no parameters and it also has no status bit, but a bit that says character available, which you do not need to probe actually if you use the pause mechanism. Then you just do a UART fetch. And if there is no character, another task will be running until finally there is a character and it gets fetched. And you don't have to do all these nasty status fetching loops that should tell you whether you can now go ahead and fetch a character. And also, as far as the baud rate is concerned, that the actual baud range you are using, I mean, you know this beforehand when you do your design, how fast your host can access the serial line. And then there is, I have just one constant in the VHD, in architecture package that has, so this should be 112.600 baud, and then the VHDL code extracts this information and sets up proper counters to give you exactly 115.600, if that is possible at all within ±3%. So that was the DAC code, which is simple because it is only in one direction. And so this gives you this capability. You have values, you say DAC store. More complicated is the ADC, and here is the, it does no longer fully, if we leave out the reset, we can almost see all of the code. Again, we have an SPI interface, so S clock is important. And so the first thing we do is, S clock is true. And then we look whether the ADC is busy at all. If it is not busy, we can write a new channel number into it. And to do the channel number is, we have to shift out 00 and then a 3-bit channel number in order to program the chip correctly. And that will, and doing this, and we also set busy to 1, and setting busy to 1 will activate the chip select input for the ADC, which means now it starts converting. And then we set the cycle to 31 because the result of the ADC conversion, for some reason which I don't remember, is actually 32 bits, I believe. But I mean, this part of the code here, this takes care of the setting the channel number and starting the ADC converter. And so if we are busy and the ADC is still converting, whenever S clock, there is an S clock transition, the shift out 3 down to 0 and 0. So this is the shift out we defined here, and now then we start working. We shift out the channel number into the shift, because we have an ADC D in that gets fed by the shift out register. We have an ADC D out that we read back into the shift in register. So at the same time, while we shift out, we also shift in the first bit of the result. I mean, this is just how this ADC converter works. And if cycle is 0, what the heck is cycle? Cycle is what we said here. So if cycle is 0, then we are done. So we first look at the code. If cycle is not 0, this is the else clause, we just decrement cycle. So what we did is we shift the out and in registers, we decrement cycle until finally cycle equals 0, in which case we set busy to 0, which means we set chip select to 0, and the sample, which is I called sample 1 here, these are sample 0 and sample 1. I don't talk about sample 1, 0 right now. This is something special. It comes later on. Not so important. So at this point, we know that whatever we have collected in the shift register up to now, plus the last bit, which we append to the right, that is our sample that we wanted to read. And then we are finished and done, and we have seen the ADC result. As you can see here, as long as busy is true, I'm not allowed to touch the ADC. So as far as the pause register is concerned, for one thing, while busy is true, there is definitely the processor needs to execute a pause if I am trying to access the ADC converter. So any questions concerning this code?
Yes. How do you call pause?
How do I pause? Okay,
yeah,
now
pause?
we are getting into the
really complicated stuff.
Into the real, well, yeah, sort of. Unfortunately, at this point, I don't think that I'm using the pause signal at all, but let's see. In the actual design, flex pause. Oh yes, we do use it. This has to do with the fact that you can use flag bits as semaphores, and you can store and fetch flags. And so if you write into the flag register, so this is this expression. And if the write data into the flag register has the most significant bit set, there must be more ands. Well, the sign bit is 0. So if it is a positive value, and the write data and the flag bits. So the flag bits width -1 is the. I have to show you this as well. So here we have basically we have in the architecture package, we have the flag register, which in the least significant bits, they are interrupts, they are interrupt capable. And so in this design, because I added this I time, this 250 microsecond interrupt, we have one interrupt source. And so I say I have one interrupt. And then for the remaining bits, there is also a pseudonym for the interrupt register, which is flag register. And the flag register returns all the bits in the flag register, whereas the interrupt register, if I do a fetch on the interrupt, it only returns the bits of the active interrupts. So if I-time is not set because the 250 microseconds have not elapsed, then int-rec fetch would return a 0. And I would only it would only return a 1 if the time interrupt has elapsed. Whereas when I do fetch via the flag register, I get the status of all the remaining bits. And this is where flag width comes into play. Here I have defined altogether 8 bits with 1 gap, which I didn't use, but this is, I can do that. I mean, the VHDL code, this will be optimized away, sort of. So this is a part of the flag. This is the role of the flag bit. So I only of the right data, I have a 32-bit architecture, but I'm only interested in the last bits there, which are the widths of the flag register. I take the unsigned value of this and the flags. Oops, the flags is flags. Just for your understanding, colon flags. If I do this in force, is flag rec fetch semicolon. So this is a shorthand for flag rec fetch. This is flags. So basically, what this expression here does, if the current flag register and the flag and the number which I want to write into the flag register, if they have no current common bits set. So let's say in the flag registers, I have set bit number 1. And in the write data, I want to probe bit number 2. And so this acts and takes care that the result is 0. So if this is unequal to 0, which means I have set previously a semaphore bit to 1, and then I want to write a 1 into it, then this will trigger the pause signal for the semaphore handling. So I apologize, this is already complex. This is complex and complicated. But basically, I mean, it gives you the capability of misusing the flag register as a semaphore register, and it does what a good semaphore is going to do. So here we produce now flex pause, which is one of the potential pause signals. So it's pretty much so. And so where do I feed this in? So this is where I feed this in. Flex pause goes into microbus pause, and then the microbus carries this information down into the instruction decoder or on the microcore entity, and then the controller will react appropriately to this. And if you have, like, say, we also have an ADC interrupt, then I would say, or ADC pause. And then I have to take care of, I have to write an expression of when this should be true, just to give you an example of what in the ADC case, or let's take the DAC case, that is easier. My cursor, I lost my cursor. Ah, there it is. because the battery in my mouse. Let's go for the DAC because this is the easier case. So if we want to add a DAC pause, all we have to do is colon, we are in VHDL. So we say DAC pause becomes 1 when. Oops. So for one thing, mu rec write from U bus, comma, duck rec, and I have to look at the code here. We know that while the DAC chip select is active, we cannot use the DAC. So all we have to do is to end this with DAC CS. So this is what we need to do. And DAC CS equals true, else 0. This basically means if the DAC is still busy, and if I want to write into the DAC register, a pause is raised, the DAC pause, and is fed into the microbus pause, and then the microcontroller acts accordingly. And I can also show you what it actually does. Here we go. A second, I have to find. Here we have this if pause equals 1. So if pause equals 1, then what we do is we do not latch the results that the current instruction, which is a fetch, has computed up to this point. We just do not want to change anything in the registers on the stack. Instead, we put the address, the program address of the instruction that is currently being, well, that is currently being paused. We stick this back into the PC, and then we stick the pause instruction into the instruction register, and then we say chain equals 1. I mean, this saying chain equals 1 means that the next instruction is not taken out of the program memory. Instead, it is taken out of this register. And so this is how the pause mechanism works. And if you look at the op pause instruction, then it does a call trap. And a call trap means, this is all so convoluted. If we go at some application code, then here are the traps. And here is the pause service routine. And so the call trap is, it goes to exactly this position, it executes a pause, and then it doesn't exit. And that's how the pause mechanism works in general.
Okay, thank you for explaining that. It reminds me very much of code in 8051 ChipForth that I was using many years ago from Forth Inc. that I spent a long time trying to work out what it was doing. And what it was waiting for a character on a UART, and if there wasn't one, it subtracted 2 from the instruction pointer of the fourth machine, went to pause. So when it came around again, it did the same thing again.
Okay, yeah, it did the same thing in software. I mean, this is actually how the...
This is actually hardware, though. This is... I like it very much. It's very,
And I mean, there's the Go programming language has also this concept as a pause embedded in the language itself, and that is also a software solution of some sort. And this all, to my knowledge, the first time I saw the pause mechanism was in the transputer, where it had been used to synchronize the serial links that you could interconnect several transputer chips with each other. So I hope I didn't change anything in this code, because that is active code.
Christian has a question.
Okay.
Okay, I have to go, Klaus, so I'll just say tschüss, vielen Dank.
Ja.
Bis zum nächsten Mal. Okay, ciao.
Okay. I'm not muted?
We can hear you.
Okay. All this reminded me of when I was working on mainframes in 1968, where we had boards that contain logic gates, other boards that contain flip-flops, and other boards that contain organized flip-flops that were registers. And then we had a wire wrapping backbone that was interconnecting all this to create something even more complex that was a disk controller. Is this more or less what we do in an FPGA with VHDL? We're just doing it differently with a different technology, but more or less interconnecting gates and flip-flops and registers and counters.
Yeah, is exactly what is happening there. In the FPGAs, you have so-called logic cells, which most FPGAs nowadays have two logic generators which take 4 inputs and can produce any logic function on 4 inputs, which is quite complex already. So basically, it is a mapping RAM table where you set ones in the 4x4 matrix, where you are setting bits when the expression should be true, and then these two general purpose logic functions are connected to a flip-flop or not connected to a flip-flop. And then these logic cells are programmable as far as what the logic function is supposed to do, and whether you are using the flip-flop or not using the flip-flop, or using the inverted flip-flop and stuff like that. And besides, then around every logic cell is an interconnect framework of interconnect wires, which are short wires going to neighboring logic cells, going medium long wires that kind of span, let's say, the next 16 cells around you, and then very long wires that go through another column or another line, and as far as the clock signals are concerned, go across the entire chip. And so that is basically it. And programming this means that you set, and in the configuration procedure, you set the bits that activate or disactivate wires and interconnect horizontal and vertical wires, and set the logic functions in the logic cells. So that is basically it. And so the configuration is equivalent to your wire wrapping the posts on the printed circuit boards.
So more or less, it's programmable wire wrapping.
It's programmable wire wrapping, exactly. Yeah.
Okay.
Nicely said. Yeah.
Thank you.
Klaus, thank you very much.
More questions.
More questions.
I think I mean, if there is, if you are curious, I could now, I mean, spontaneously define a new input register or a new register that you can save a value in and that you can read back, nothing fancy, just this, you can save something there, which is not saved in memory, but in a register and read it back. And then you can see step by step what needs to be done to the VHDL code in order to enable this. And this is basically, I mean, the list of things you can see here, but seen in reality. So I want a yes, at least from one person. Okay, it seems we are done for today.
Yeah, I think it's a good idea to look into this at some future meeting, and learning that the starting guide is online. I would assume that lots of people that have the appropriate FPGA board will bring it in, and then maybe we can also get some hands-on workshop where people do it in their own setup as well. So that could be very interesting.
That would make a lot of sense. I stop sharing at this point so I can see who is.
We don't need to stop our meeting, but we can stop the recording now, so we have a little time to make a free chat if you like.
Yeah. So that goes like this.